Welcome everyone to Biodesign Challenge Summit 2021. I'm Dan Grushkin, Executive Director.
I'm Veena Vijaykumar, BDC's Program Director.
This is our staff. This is Alex Kozalewski, our comms manager. And I don't know if everyone's met Emma Hill, but Emma Hill is our newest employee, our program associate. Go ahead, Veena.
All right, thank you, Emma and Alex. We'll see you guys very soon. In case everybody wants to know the faces of BDC for the rest of the summit, that's for you. Anyways, all right. We want to say hello, everyone. Thank you for joining us. I'm not sure how many of you are out there right now, but thank you for being with us this morning in New York City, evening or night, wherever you are. So we're going to jump right into it. So at last year's summit, I said in front of you all, just 3 months into the pandemic, filled with hope after seeing what our students were able to accomplish when faced with such a daunting challenge, such as learning during the global pandemic. This year has been no different. The majority of our classrooms ran their entire academic year online, with a few attempting hybrid learning. And our students, instructors, mentors, or supporters, they all met virtually all year long to collaborate on their biodesign projects with little to no access to their studios and their lab spaces and their classrooms. Yet here we are with 51 schools having participated in this year's challenge more than ever before. The students have spent countless hours reading scientific papers, reaching out to experts for feedback, interfacing with the communities that they're designing for, and developing materials to communicate their research and designs with you all, our community. So yes, the students have filled me with hope once again that humanity can be resilient, it can be thoughtful, and it can be kind. I hope as you watch these presentations over the next 3 years that you too will feel this hope. So before Dan speaks, I want to go over a few logistical details. Since we can't be together in the same room this year, hopefully next year we will. But this year we've asked each of the students to create a video about 5 to 10 minutes that will explain their project for you. We will be broadcasting those videos, each from each team, and then the judges will have the opportunity to do a live Q&A session. We're all here in Zoom together, so we'll be able to kind of speak to each other, and the students will be able to answer questions and clarify different things from their project. While you watch the student videos, we have put all of these things that I'm about to mention will be right below on if you're watching on the summit page, but we have a few ways that you can engage with the rest of the community. So as I said, if you're watching this on the BDC Summit page, you'll see all of the links and everything that you would need to join all of these things. Firstly, you can add to our virtual community Miro board. So we created a large Miro whiteboard for you to be able to interact with and answer questions and tell us where you're from in the world, where you're watching from, all sorts of things. Show pictures of your pets, lots of fun ways to engage. Secondly, we have opened up the Community Choice Prize. This is a prize we started a couple of years ago, actually last last year. And if you have a team that you enjoyed very much as you're watching all of these student projects, we ask that you vote for your favorite project, and we'll announce the winner during the award ceremony this Friday. Thirdly, follow us on Instagram and Twitter. Join us on social media and share your experience. We are at Biodesigned with a D. And you can hashtag BDC 2021 as well for anything that you may be sharing. And lastly, we have a gallery show this year. So the Biodesign Challenge in past years has had a gallery show where the students are able to interface with the general public and answer your questions that you may have, any burning questions that you want to ask. So we hope that you'll join us. The virtual one this year is this afternoon, New York time. So it'll be 3 p.m. to 9 p.m. Eastern time. And each finalist team will have a table, and you can ask them questions about the project, as I said, mingle with other guests at our community table, whatever it may be. You're welcome to join us. So links, again, all the links are on the BDC website. That being said, let's go on to Dan.
Thanks, Vina. Well said. Students, instructors, mentors, sponsors, give yourself a round of applause. This year has been another crazy one. So thank you for doing this again with us. We're so excited. I can't wait to see your projects. And as always, we're incredibly grateful. A little bit odd, as usual, at all the hard work that you've done. So really, thank you so much. Before we go on with the show, I have some thank yous to make. I should just start by thanking the team, the Biodesign Challenge team that has just gone unbelievably above and beyond, have been working day and night to make this event and this program possible. Really, you guys are the best team. It's been just a pleasure to watch you go. All right, moving on. I should thank our sponsors. This year, Barilla has been a new sponsor. We have a prize specifically that we worked together with Barilla to create. It's called the Regenerative Living Ecosystems Prize. We have a number of great projects that are going to be competing for it. It was really just a meaningful collaboration with them. And I'm really excited for you all to meet the judges who will be on later this week to evaluate the prizes or evaluate the teams. I should also thank Science Sandbox, who is back with us, I think now our third year in a row. Amazing collaborators and really supporters of what we're doing. They also have a prize, which is about public engagement. I'm excited for you to see those prizes or those teams as well. National Endowment for the Arts is back with us again. So thank you, National Endowment for the Arts. A big thank you to Ginkgo Bioworks. Ginkgo has been with us since day one. Christina Agapakis has been on our board for many years. What can I say? It's just been a really intense, interesting collaboration. And I should also say that at 5 p.m. today, Christina and Grace from Ginkgo will be giving a talk during our gallery show. So do check that out. Okay, moving on. Sorry, I have notes here. There's a lot of people to thank. I don't want to miss anyone. Of course, there's Twist Bioscience, also back after many years of supporting us. Welcome back, Twist. There's Ecovative Design. Actually, Grace Knight from their team is a judge this session. So welcome back, Grace. SOS Ventures, thank you so much. And then another one, which is really cool, is Alginate. Yeah, Alginate. So winners of the first year of Biodesign Challenge in 2016, they've come back as sponsors. They now have a full-on company making yarns from algae. I just got a text from Alex, their COO. I don't know what it says, but hi, Alex. And thank you again for being with us. Minji's one of the judges, also from their team. And then, of course, I should also shout out Argus HD, who's back with us this year. Thank you, Jeff, who's behind the scenes. Thank you, Mark, who's behind the scenes. You're not going to see them, but the only reason why this is happening as smoothly, hopefully as smoothly, as it will go is because of them. So thank you both, and thank you, Argus HD. Okay, a few updates for you. This year, we celebrated the first anniversary of our online magazine, Biodesigned. That's Biodesign past tense. Check it out if you haven't seen it. There's some really great articles in there. And honestly, the members of this community are its contributors. So if you want to see what other people are thinking about, their deep thoughts, their projects, where they want to see biodesign go, biodesigned.org is where to check it out. Also this year, I just want to shout out our hubs. So we created Biodesign hubs. These are regional hubs where folks from different areas of the world, geographical regions, get together, present ideas to each other, find collaborations, share resources. We launched it this year in Europe, Latin America, and the Midwest United States. Each one of them had an event that brought together some of the most eminent voices in their regional communities. And again, just a total inspiration to see what they are doing and how they're developing their ideas. So if you're in one of those regions or you want to create a hub, feel free to reach out to us. We are going to be building out that program in years to come. Finally, last thing, and this I think is the biggest and most exciting for me personally. I've been working on this now for over a year. Biodesign Challenge is about to launch a book. And so the Kickstarter for the book project literally launched this morning, less than an hour ago. It basically includes 100 plus voices from our community, writing about their projects, writing about what they see as the future of biodesign, writing about what this discipline means to them and where they hope it will go. So if you are on our website, you'll see a link to the Kickstarter. Please check it out. We made a really adorable video. If I do say so myself, I check it out. And buy a book. I can't think of a better way to encompass the last now 6 years of biodesign than with a project like that. So, celebrate the community, celebrate the projects, learn something from the eminent practitioners who are in there, and really be part of it. I really do think you'll enjoy it and get a lot out of it. I'm not going to give a long introduction. I've kind of rambled on. But if you want to sort of hear our thoughts and about the last year and where we think Biodesign Challenge is going, there's a director's letter also on the website. We spent a lot of time thinking about what we wanted to tell you. I encourage you to take a look at it. I don't want to steal from the students. Really, this is about them and their work. And so I'm just going to pass it back to Vina. She's going to be emceeing this morning, and we'll get rolling. It is so good to be back with you. I'm looking forward to this entire week. Thank you.
Yeah, thank you. Yay. All right, we're going to go right into it. Again, thank you everybody for joining us, and here we go. So we're going to just start right with LaSalle College of the Arts. Jeff, whenever you're ready.
Shell Decay explores decay as a process of material treatment on food shells to innovate new materiality. Human making is where human conducts experiments on different types of food shells to allow nature to design and make afterwards. This project aims to pursue a world that humans and nature could coexist. The notion of decay was inspired through a conversation with my grandma during breakfast. When I was about to serve my grandma a slice of bread, I realized that the bread was moldy, hence I wanted to throw it away. But my grandma scolded me for that and said that I was being wasteful. She said that if it is moldy, just simply heat it up and the bacteria would die. and it will be clean for consumption. That actually made me wonder. In the past, humans interact with materials directly, allowing materials to speak to them, while in the present time, machine acts as a barrier between humans and materials. Humans are simply shaping materials based on their own impression, disconnecting themselves from the material's actualization. How could we draw closer to nature? We first have to unlearn our cognitive impression that we have for materials and allowing nature to speak to us. As a communication designer, I lean more towards visual learning. Hence, I gave nature 40 days to work on 12 types of food shells and flash in hope to understand how nature would design. And through that 40 days, I learned that when something deteriorates, something else prospers. Decay could be as constructive as it is destructive. Nature has its own color. In this case, nature turned pineapple from yellow to reddish orange, lemon from yellow to off-white, and banana from yellow to black, then white. So the question is, how can we manage decay? There are a total of 5 contributing factors that affects the rate of decay, and the 5 factors are nutrients, space, acidity, temperature, and humidity. What will promote growth? More compatible nutrients, more space, higher acidity level, an ideal temperature, and high humidity. There are many different types of shells. Each functions and adapts differently. David Pye mentions that good materials weren't found, rather it was being made. I believe that it is the same for material of waste. It's up to our sensitivity to pick our resources and turn them into good materials. In this diagram, I learned that because of pollution, marine lives are suffering as the pollutants are competing nutrients with the shells, and those shells are mainly made out of calcium carbonate. It gave me the impression that humans construct concrete buildings and structures to protect themselves from the harsh weather, while nature constructs shells made of calcium carbonate to protect themselves from predators and erosions. Could calcium carbonate be nature's form of cement? That's when I wonder, where can I find a food shell that is high in calcium carbonate and also abundant? I looked into my fridge and I found eggshells. Eggshells are made out of 95% calcium carbonate and they are also abundant due to consumption. In my region, Singapore, being a developed country with lots of businesses and office workers, coffee is highly consumed, thus producing large amount of coffee waste that are oftentimes thrown away and underutilized. I wonder, how can we optimize our waste? I started experimenting on eggshells first with a recipe taken from material room, where sodium arginate is being used as a binding agent and vinegar as a curing agent. The material is very hard, yet very brittle. It almost feels like cement without sand. With that, I wonder, could eggshells be our cement, while coffee chaff be our sand? I worked out a diagram that draws the interaction between these two waste materials that never met nor interact, and based on their atomic structure, could the mixture be more structurally sound? I reconstructed the recipe by introducing glycerine and coffee chaff. The material was then being molded into various thickness to observe its strength and durability. To my surprise, the material is slightly flexible and does not break as easily as the eggshell. I tried coating the material with sodium arginate, which is the binding agent. The material actually cures as a layer of bioplastic, which is water resistant, and it could be used to bind broken pieces back together. Now that I have seen that the material can be molded, I wonder, could the material be printed? I readjusted the ratio of the recipe to allow the material to be printed smoothly. Now that I have learned the process of human making and nature making, could an alliance be formed between humans and nature? The blue section represents human making, while the red section represents nature making, and the yellow represents collaboration. The question is, how can they collaborate? Based on Singapore's NPark research technical notes, I learned that Singapore's soil lacks nutrients, and with that, human design and interaction between matter, which in this case, coffee chaff covers the primary nutrients of soil fertility, while eggshells cover the secondary nutrients needed. By selectively placing the materials, I learned that eggshells would turn green when interacting with the mixture of coffee chaff and eggshells. Nature designed and colored the eggshells through growth. What if I change the colors of the eggshells? How would nature color it? What if I bend and give it structure? How would nature adapt? And what if I allow airflow? That would slow down the deteriorating process, allowing the eggshells to retain its color. With that, I made a mini prototype out from the material and designed it for the first few days while allowing nature to design afterwards. Printing structures, which are the source of nutrients and backbone. Filling the gaps with eggshells, which hinders the growth at that area. Vinegar is used as a curing agent to fix the shape of the material. After the curing process, drain out the excess vinegar and rinse it with water. During the drying process, the material can be bent to take up another form. After it has been fully dried, coating it with sodium alginate at the top would allow water to flow to the gaps, reducing the chance of foreign bacteria to grow above. The bottom is not coated with sodium alginate to make it exposed, allowing nutrients to seep into the soil. Seeds are then planted and the prototype is being placed on the surface. This is just one experiment of how we can use food shell waste to work with nature. There are so many types of shells out there left for us to experiment with, and I can't wait to see how nature will surprise us through design.
All right. Thank you, Johnson. And thanks for being with us today. So we're going to start go directly into the Q&A. So if any of our judges have questions, looks like Beth has her camera on. Do you have a question, Beth? We could start with you.
I'm happy to start. Thank you so much for your presentation. It was beautiful. I love the design creativity. It's really nice to see it in action. Some of the criteria for the judging are around risk and safety and dual use stuff. And so I wanted to hear you speak a little bit more about some of the potential harms that you could imagine your technology might create inadvertently. Yeah.
Right. Okay. Thank you. So for decay is a very sensitive thing, which I personally, like my whole room stinks very bad because I do it at home. I can't go to school. Yeah. So I suffer that 40 days of decay. So what you said, it really makes sense. So what happened is when I planted it down, I planted the eggshell and coffee chaff. It is so highly, there's so much nutrients that you'll start growing mold at the side of the soil, which is one factor. Therefore, I coated with sodium alginate to selectively degrade things. Yeah, so that I will only select where I want it to grow. And same for the eggshell, because there's so much calcium, it wouldn't promote growth and it hinders the oxygen level. Yeah, so with that, actually, we can actually play with where we want to grow things and where we don't want to, based on that 5 decay factors. Yeah, hope that answers your question.
Denise, would you like to go next?
Sure. I think it's very interesting the way you're combining a kind of soil remediation proposition with this aesthetic device. And I'm wondering how you imagine the patterning and the form making that you're talking about with the sheet of material influencing, whether it's cropping and what scale you're thinking that this would play out at. How do you imagine this? Is this a garden or is this a field?
Okay, so firstly, this material is created to help Singapore's soil because Singapore's soil lacks that 2 types of nutrients. Hence, I'm just seeing it as a surface level, but it could also be mixed inside the soil. However, it will be too fertile, which it will make the whole soil go moldy. Hence, I thought of just putting it at the surface where we could expose the areas that we want and the areas that we don't want. Yeah. So like what you say, I'm just seeing it as a surface, here on the surface. Yeah. Thank you.
Margaret, go ahead.
Yeah.
When you're
Yeah.
Great presentation. I'm really interested in your research process. It strikes me that you've done an incredible job of materials research, kind of through sort of making and doing and seeing what happens. And a little bit, there was a little hint of some like reading research a little bit, but I'm curious, a lot of what you've come to is absolutely what happens when you talk about decay of materials. And, in my world, I come from a scientific background. So I would say temperature towards decay is thermolysis. I would say humidity is hydrolysis. There are scientific precedent behind this and how these mechanisms work. So as you go on in this, you've clearly learned a lot, but how might you go about, what kind of research have you done, and what kind of process might you further do if you want to get further in this project and really understand some of the scientific underpinnings, because there are quite a bit. How might you go about that?
All right. Okay, thank you. So yeah, like what you say, I'm coming from a designer point of view, which I don't have any scientific background. Hence, like my recipe was like inspired or taken from scientists, like to aid my process. So my process is done like practice-based research, where I work with materials and I learn through the process. I learn through making. And for theoretical aspect, I reference like Neri Oxman, where she talk about material ecology, where she talk about when you print small, you can print big, and research paper, not so much of research paper, but more of like thinkers. Yeah. So how will I think that I want to further this is I would want to work with material scientists. I want to work with a team, because now I'm working alone. So to further this, because I believe that in my own discipline, I really lack understanding of my processes. Like what you say, like more scientific term. And for me, I'm just seeing the surface level, just the tip of the iceberg. Yeah, I'm just seeing all the visuals. So I want to work with scientists, engineers, artists, and people that will make it applicable. Yeah, thank you.
Let's do one last question from Karen, please. Karen, when you're ready.
I was excited to see the design aspects that you had here. I'm wondering, when you were looking at the landscape of research, where you felt that this fit in as a kind of innovative project in terms of reuse and recycling of materials. We know that this is definitely a trend in biodesign at the moment, and just curious as to what brought you to eggshells and to calcium carbonate as a material.
All right. Okay, so the most initial one is I was inspired by parrotfish, where because I found out that parrotfish eat coral reefs, and they made like 80% of the beach, of the sandy beach, is actually parrotfish poop. Yeah, so I got very interested, because it's like they consume it, then they poop it out, then it's a material that we want. And Singapore actually lacks land space. So Singapore somehow like buy sand overseas, then reclaim land and so on and so forth. So I'm wondering what if humans produce waste like eggshells and like food shells specifically, and that could be our land, like in Singapore, but that's like very speculative. Hence, I took a step forward and try out one first. So yeah, so that's what made me choose eggshell also somewhat. Yeah. Thank you.
Thank you, Johnson. Thank you, judges. You all can take your video off for now. So we're going to move on just to the next team. Again, congratulations, Johnson. We'll see you soon. The next team is University Teknologi Mara.
clarify, Nashamira binti Sharumizam, and we are the UITM representative team. Our supervisor, Mrs. Natrina Marian Pitoyong, also the UITM representative team, and our advisor, Dr. Patricia Niva, majoring in mechanical and mechatronics engineering. Lost touch. On December 31st of 2019, China alerted the World Health Organization about the several pneumonia cases in Wuhan, with no death counts. As the time goes by, on January 2020, China announced their first death of the outbreak, and this leads to the cases outside of China. Thailand have been reported by WHO to have the first cases outside of China. This started widely spread to South Korea, Iran, Italy, Europe, and other countries and continents, following in February 2020 with their own outbreaks. On March 11, COVID-19 was announced as a global pandemic by the World Health Organization. At this point, COVID cases and death counts have arisen worldwide. COVID-19 is a contagious virus that spreads through the human touch, droplets, and aerosol. This means talking, singing, coughing, and sneezing have much of a higher chance for the virus to spread to other people. This COVID virus outbreak can jeopardize the human body really fast, especially to the people with low antibody, followed with the other health complication, particularly the senior citizen aged 60 years old and above.
Hello, my name is Adam Yusuf bin Muhammad Zambi. First of all, our theme of the project is the lost touch. User will feel the warmth and grip of a handshake when they meet digitally. They can feel the softness of fabric in online stores as well as the texture of rough surfaces of historic buildings when touring virtually, elaborating on this concept. As digital meetings, AR and VR technology advance, the project envisions application in a variety of domains. The next slide is possible technology. The first technology is haptic technology. Haptic technology, additionally referred to as kinesthetic verbal exchange or 3D touch, refer to any technology that can create an experience of contact by using applying forces, vibration, or motion to the consumer. The second technology is visual sense. Is a technology that uses sensors to collect information by detecting the physical, chemical, or biological belongings portion and convert them into readable signs. The third technology is augmented reality. Is an interactive enjoy of actual international environment in which the object that live inside the actual global are enhanced by computer-generated perceptual record. And the fourth technology is touchable hologram, which is ultra haptics. Ultra haptics include a tool that could select up ultrasound waves present within the air, condensing them to create a pressure distinction that gives the illusion of a touchable 3D item floating in skinny air. And the next technology is heptaclone. Heptaclone, which is haptic and optical clone, is a progressive interactive device producing haptic and optical clone photo in mid-air. And the last technology is electrovibration. Electrovibration is primarily based on an impact in which touch receptor within the pores and skin can be dubbed into perceiving texture.
Hi, my name is Muhammad Nizar bin Ahmad Yahaya. For the sketches and the design. Function and purpose of the product. Graspable, touchable, wearable. Since the pandemic began, touching is unnecessary. The public surface is 90% possibilities for humans to touch just to see what we feel like. This glove can reduce the spread of virus because it is not direct human contact to the public surface. This smart glove can feel the surface and grab the feel of labor without touch. This smart glove can replace hands to touch objects. For shape and form, this smart glove is designed into the shape of human hand. This smart glove will fit to the hand for easier grabs. For the material, main data reading, we use plastic made. For the data circuit, we use flexible steel wire. For the receptor plate, we use rubber coat. For the casing, we use synthetic leather glove. Color and texture. The main reading will be covered with matte plastic and carbon. For the receptor plate, will be covered with silicone grip as the nature of the hand to have grips or fingerprint.
Hi, my name is Harisazik bin Muhammad Jais. For material and component, we use leather gloves, while on the part to be touched, it has a thin thickness for sensitivity. On the finger, there is a steel electrode that's sending data to piezo. Piezo is located on each part of the glove's fingers and palm, including the fingertips. Its function is converting electrical charge that produced by sound form into energy and sending the output to the fingertips. In the active data box, there is an electronic film that translates data into texture or fields. System and technology. This is the system and technology used by these haptic gloves. Haptic energy is used as kinesthetic communication that can create an experience of touching by applying force, vibration, and motion. Graspable device is to give a feeling of movement, position, and force mediated by nerve, not just in our skin but also in our muscle, tendons, and joint. Wearable device can give the impression depending on the tactic sensation pressure, friction, or temperature mediated by skin nerves. User can feel the touch and texture and control their hand without touching the object. This is the usage scenario for haptic glove. Anne is a fashion designer and she has used this haptic glove as a tool to serve her customers. By wearing glove, Anne can feel the texture of the fabric without touching it, and her customer will be able to feel the texture of the fabric through online. The customer can feel the same fabric texture as well through the glove. This is the 3D model of the glove that shows the actual shape and form of the gloves. At the top of the glove fingers, there is a thick section to protect the steel electrode from being damaged. Steel electrode is located inside the glove where it is shaped according to the user finger to connect the piezo to the active data box. Active data box plays an important role in translating the input data that's sent by piezo. It is located on the back of the gloves.
Hello, my name is Norauda binti Sharana. The research, we were excited to explore the concept of physical sense that can travel through material. Dr. Niva, the expert we consulted, provided us with a great overview and understanding of the list technology we had shortlisted. The idea is feasible, but we required very high technology in the future. We wanted to develop our appreciation for it when merged with design practice. We found an article on interesting material research. Thin plastic structure with organic detail that can control direction and reflection of sounds with a pretty high frequency. The study revealed class of material is called metamaterial, artificial material that manipulate wave. For example, while the particular metamaterial is made of 3D printed plastic, it's not the properties of the plastic that are important. Some interesting findings we discovered. First is some vibration travel in wave pattern. Number 2, the vibration are transferred to the air surrounding the structure, create a sound wave. Number 3, the speaker makes the air around it vibration. Now, and the last, when a loud sound moves through the air, it makes other objects near it vibrate. Finally, as we discover, the certain succession of the palm can provide different succession. We believe that the different type of sounds can be used to coat these various surfaces into different texture through the vibration into sensitive surface. Overall summary. Haptech Glove, the point of project to bring back the concept of touch. According to researchers, can only transmit emotion through touch. Touch is essential for social communication and connection. In our opinion, this lost touch creates a product that has advanced technology that will be beneficial in the future. Lastly, we expect to be able to live like a regular life with no limit on certain activity, but still keep living in a clean environment and stay hygiene. Thank you.
All right. Thank you, students. If the judges have any questions, please.
Excuse me, the host is still blocking my...
Give me 1 second. Let me allow. Okay. Go ahead, Margaret. Yeah.
Great presentation. So while watching your presentation, I couldn't help but think about...
Excuse me, my mic too. My video can turn on. Okay. Okay.
Is the team ready? Yes. So while watching your presentation, I couldn't help but think about the fact that we've live in a global society. We've known this for some time, and that's very evident by the digital sphere that we are operating in right now. But the pandemic has been a global shared experience in our real lives, in our touchable, tangible lives. So I think coming to this idea of a glove, something that is sort of a connection between, that digital sphere and a very physical, touchable, tangible place in our real lives is a wonderful place to begin. I'm really curious about, and I don't know what kind of conversations you've had around this glove about, beyond the example you gave of a sort of a situation in commerce where a customer could touch a fabric and see how it feels and experience the material that way. Have you talked any about the sort of cultural or ethical ramifications of how a glove like this could impact people? Because we're in this sort of place where we haven't been able to connect and touch, and there's an emotional, social component to that as well.
Okay, first of all, my name is Champaign, and you can call me Aina. And the original idea is from the glove is actually we found that every things we touch, it have different frequency and the sound vibration. So the original idea is let's say if I touch a soft surface and a rough surface, the sound wave will be different. So from the sound wave, we wanted to code the sound, and then if let's say people buy a silk textured a silk textured and a cotton textured what do you call it, fabric, and then they could actually feel the haptic on their fingers. They want to feel the haptic on the fingers.
Are there any thoughts beyond commerce, though, or have you had other conversations?
For the technology, yeah, because before that we don't have any background on, especially on sound engineering. So we asked Dr. Patricia Niva on engineering and mechanical, and she said the most that have the potential one is the last technology on the slide, I think. that is have the most potential one, because every sound have their own frequency, and every sound also have their wavelength.
Beth, go ahead.
Yeah, I wanted to ask about accessibility of this technology. How expensive could you imagine it might be, and who might be able to actually use it?
About the cost, I think it's quite expensive, because we haven't done the real the experiment in a long run, because we still need to add on our research and the experiment itself, whether it's actually work on the other side, because right now in Malaysia we are still on our MCO duration. So it's tough, but about the cost, it will be costly, but my idea is I want to make this as a service, so it will be spread to all, or everybody can use it.
All right. We could do one more question from Ben.
Sure. No, I like the concept, and I understand, it's growing out of the response to the pandemic. Do you think that the need for this kind of product would go away after the pandemic, or how do you see it evolving?
Thank you. So actually, this glove, the idea is come up because in Malaysia we have a variety of ceremony that we need to shake hand with other people to, for example, as a Muslim in Malaysia we have Idul Fitri celebration, which is we before pandemic we gather together and have a session that we ask for forgiveness with handshake. So during this pandemic we cannot do this kind of thing, and we only can make a video call, and it never feel the same like in face-to-face action. So this product we made it not only for Malaysian or other Muslim, but for other country if the distance make being an issue to they make any contact. So
thank you.
So people can meet each other across the world, becoming more and more global. Cool. All right. Thank you, team. Thank you, judges. I know it's really late in Malaysia, so I really appreciate you all being here with us. So have a good rest of the night, and we'll see you very, very soon. We're going to go right into our next team, which is Donghua University.
Here is our biodesign. Amphiphilic phosphorus dendron-based micelles encapsulated curcumin for improved therapy of acute lung injury. What we present here will be an introduction to the design background and our proposal. Part 1. Background. Acute lung injury, ALI, is a symptom happens in many diseases related to lung damage. It comes in this way. First, lung damage can result in inflammation, and this inflammation can spread to the alveoli, thus decreasing the lung's ability to provide oxygen to the body, and finally result in the symptom of ALI. ALI is also a main symptom of critical patients with COVID-19 and responsible for up to 35% to 40% of mortalities. So in this context, improved therapy for ALI is especially essential. How is the treatment for ALI nowadays? we have two kinds of traditional treatments. First, the medical treatment, by taking medicine orally or by injection, but this usually has unavoidable side effects and low drug bioavailability. Second, we have mechanical ventilation therapy, but ventilation is always difficult to control, and excessive ventilation can easily cause lung injury. On the other hand, the way of drug administration also plays an important role in ALI therapy. And generally, we have three kinds of administration mode nowadays, in which the aerosol inhalation is more convenient to use and beneficial for repeated administration. So in this context, the development of innovative drugs for the treatment of ALI is still an urgent need. Regarding this, the involvement of nanomedicine might be a good choice. With smart design of nanomedicine, we can achieve high drug loading efficiency, combination of different functionalities, as well as multimode therapy or diagnosis of the diseases. Then, part 2, let's introduce our proposal. Within the pathogenesis of ALI, the alveolar macrophage is a potential therapeutic target. And our focus is to cure ALI by reducing the alveolar macrophage-mediated overexpression of pro-inflammatory cytokines and reactive oxygen species. For this purpose, we have our nano design. We constructed a nanomicelle using TBP-modified amphiphilic phosphorus dendrons to encapsulate the hydrophobic antioxidative drug curcumin, which is a traditional Chinese medicine. In order to check the therapeutic effect of our designed nanomedicine, we performed cell experiments. First, we checked the ROS levels in activated macrophages with different treatments. Here, the red signal represents the ROS detection probe, and the blue signal represents the cell nucleus. And the weakened red signal showed that our nanomedicine encapsulating curcumin could lead to a much better antioxidative effect than the free curcumin. After that, we applied a Western blot assay to evaluate the mechanism of our therapy. From the results, we discovered that our designed nanomedicine downregulates the NF-kappa B activation in cytoplasm, thereby inhibiting the transcription of cytokines related to inflammation. For further study, we performed experiments at the animal level and applied micro-CT and HE staining to evaluate the therapeutic efficiency. We are delighted to find that the nanomedicine is also effective at the animal level. Here we also have an animation to show the process of our animal therapy.
In our study, lipopolysaccharide, LPS, was applied as stimuli to establish mouse models with acute lung injury, ALI, for studying the therapeutic potential of our developed nanomicelles. Then, through an intratracheal aerosolization administration, the nanomicelles, which incorporate curcumin, an antioxidative in traditional Chinese medicine, are delivered into the lungs of ALI-bearing mice. Going deeper, the nanomicelles get their ways into the activated alveolar macrophages in the lungs and release the curcumin entrapped inside, which lead to reduced expressions of pro-inflammatory cytokines, as well as downregulated levels of reactive oxygen species. As a result, the ALI-bearing mice turn healthy again and are no longer suffering.
Taking the results together, we come to 3 conclusions. First, by constructing the nanomicelles, we improved the water solubility of curcumin and increased its bioavailability. Second, our nanomedicine effectively reduced the ROS generation and inhibited the NF-kappa B pathway in alveolar macrophages. Third, our nanomedicine realized at the same time an anti-inflammatory and antioxidant therapy of mouse ALI in vivo. Last, we want to thank to our instructors, Professor Shi and Professor Li, and many thanks to all the participating teachers and students. Thanks for watching our presentation.
All right, thank you, students. If we have any questions from the judges, please feel free to open. All right, Ben, please.
Great. No, thank you. Looks like you clearly put a lot of work into that project, a lot of lab time and experiment time putting that together. Congratulations. So my understanding is that the micelles improve the essentially the solubility, the bioavailability of the curcumin. So my question is, when you encapsulate their curcumin, do you have a sense of how much is encapsulated versus still free, curcumin? Because I guess when you're delivering the, into cells or into mice, you might have a mixture of those two.
First of all, I'm sorry for that. My computer is kind of in trouble, so I share the screen with my friend Jean. And thanks for the question. And for the entrapment of curcumin, we have to calculate the loading efficiency in our nanomicelles, then to perform the further experiments. This is the first question. And for the you mean the dosage for the mice experiments, for example?
Yeah, the dosage, but also how much is within the actual micelles versus still free in solution.
Oh, okay. Maybe Jing can answer this question. Actually, we have about 20% of curcumin loaded within the nanomicelles.
Okay, thank you.
Do we have any other questions from the judges?
I can ask a follow-up question as well. So when you add the micelles to the cells, how much is how does it enter the cells and get released inside the cells? Does a lot stay outside the cells, or is there a process where it's kind of directed inside the cells?
Okay. Actually, it's a process. You mean actually the nanomicelles loaded the curcumin. First, the nanomicelle get their way into the cells through the cell membrane. And through this transmembrane activity, the nanomicelles get into the cells first. Then it's released the curcumin inside. As shown in the videos, the micelle gets in and the curcumin released.
Thank you.
Thank you. We'll do one last question from Margaret. Thanks, Margaret.
Nice presentation. A lot of work has gone into this. I'm curious, so it's evident that there's, a lot of lab work and scientific component to this, but can you describe a little of your process of how you brought design into this, design ethics or ethos into your project?
Okay. Actually, as you can see, some mechanisms within our design for nanomedicine is hard for us. It's hard for people who don't learn biology to understand. So we actually collaborate with the students in the fashion college, and they did the design a very simple animation to show the concept of our nanomedicine. And I think that's a major design. So there is actually two types of design within our project. First of all is our design for nanomedicine, and the second one is their design of the animation.
Cool. So it's like the science and communication component. Great. Thank you so much, students. We're going to move on to the next team, which is the Hub for Biotechnology in the Built Environment.
Hello. We are GeoBlue. We've designed a small-scale sanitation option to assist with handling and treating fecal waste in Dharavi, an underserved community in the city of Mumbai in India. Like many underserved communities around the world, Dharavi faces systematic issues related to water supply and sanitation. The greatest challenges are caused by compact architecture and limited resources. These issues must therefore be considered in designing any solutions to water issues for the people of Dharavi.
Hi, I'm Lakshay Nair, a biochemist studying engineering.
And I'm Florian Kincaid, and we are the co-founders of GeoBlue. Our motivation for this project was to help those in need and advance scientific and engineering concepts, utilizing skills we've developed during our graduate studies.
As scientists and engineers, we approach projects with a very technical lens, but the Biodesign challenge ensured us that we integrated responsible design for a more holistic approach. We needed to incorporate an array of elements to be socially conscious about the impact of our technology. The following computerized voices represent the collective input of us as designers and engineers, and the organizations with whom we have interacted with throughout this project.
To incorporate the cultural context and experiences of the residents of Dharavi, we invited non-governmental organizations to discuss many problems faced by the residents.
Hello, my name is Parvati, and I work for an NGO. Millions of people in India lack access to clean water and sanitation. Existing plumbing is often open to prevent pest breeding. Dharavi also lacks basic provisions such as running water, electricity, and a sewage system. Poor sanitation and open sewers lead to untreated water, aiding the spread of disease, with around 4,000 cases of typhoid contracted every single day in Dharavi alone. The streets of Dharavi are compact. More than 10 people may sometimes share a 45 square meter hut. Individual toilets are therefore not common. Communal toilets often require fees for access and are unmaintained and unsafe for women. High incidences of violence and sexual assault further discourage their use. Meet Apurva. Apurva waits in line for hours every day to collect water from a well supplied by the government. While in line, she meets her neighbors and friends. Her friend Rhode is having trouble with the water system today.
My son and I spend hours every day traveling and queuing for water. Today he is ill, so I must carry it alone.
Other ways of getting water, like informal access points or purchasing overpriced water from vendors, don't help either. Once Apurva is home, she and the other residents find issues with storage. The water requires a lot of room.
As illustrated by the experiences of Apurva and Rhode, the residents of Dharavi face a variety of multifaceted issues. We considered the following key design parameters: use of locally available resources, overcoming reliance on centralized infrastructure, cultural and safety considerations, portability for easy implementation in locations where space availability is scarce and inconsistent, high energy efficiency, and to grant agency to end users to maintain and operate the product largely independently. These criteria limit the use of existing technologies. For our resources, We looked no further than the two greatest sources available: the ocean and sewage. Desalination of seawater requires energy, which may be produced from human excreta. Thus, our initial research led to analyzing bioelectrochemical systems such as microbial fuel cells. These exploit certain bacterial species' natural metabolism to produce energy from the organic compounds found in sewage. In the next stage, microbial desalination cells utilize this energy to demineralize saline or brackish water. GeoBlue uses electroactive bacterial communities that can withstand extreme chemical environments. The bacteria in these communities oxidize substrates such as acetate, and transfer the electrons gained onto an electrode. The flow of electrons from the negatively charged electrode to the positively charged electrode results in an electrochemical gradient, causing ions to be attracted to the opposite electrode. The ions separate as the membrane prevents water flow across compartments, which causes demineralization. We integrated this principle into a single-family water closet which addresses both space and gender segregation requirements. This design consists of 3 quart-sized microbial desalination cells able to process up to 2.5 US gallons of concentrated sewage sludge per day. Concentrated sludge continually flows through the first compartment, which contains a biofilm-covered carbon-infused electrode. In the third compartment, a constant flow of saline water forms a concentration gradient using the electricity generated in the first compartment to separate out negatively charged ions. These negatively charged ions migrate from the third compartment through an ion exchange membrane into the second compartment to form a strong highly alkaline brine. This indicates strict electrochemical separation between the sewage and seawater flows. The ionized portion of the demineralized water in the third compartment is transferred through a proton exchange membrane into a fourth compartment. The ions can react here with oxygen to form pure distilled water. The cells produce concentrated oxidized sludge and brine. The modular design allows the user to shut off supply to each individual cell. This simple and effective isolation system allows for easy repairs, maintenance, and reduction of costs while also preventing the system from stopping entirely in the event of a single cell or component failure. The GeoBlue water closet costs approximately $300 per unit with an average design life of 1,000 cycles, or 3 years. Now we can observe how the GeoBlue water closet would operate in Dharavi.
The implementation of our GeoBlue water closets have the potential to dramatically improve the lives of many of Dharavi's residents.
Now I wake up every day, able to visit the washroom, and then head to work. I have already got water after all. I only have to go and collect water from the sea when I return in the evening.
The seawater is poured into a compartment and potable water can be drawn easily via a tap.
The system we designed also minimizes waste by the microbial desalination cell. For instance, the brine can be used to produce alkalinity-activated cement, reducing carbon output of construction.
To deliver replacement parts and collect the waste produced by the system, we propose employing individuals who currently work as sewage cleaner. These extant jobs are often hazardous and are done with little to no personal protective equipment. By employing these individuals, our system provides a safer job alternative without necessitating difficult skill transfer.
The sludge can be dried and sold to major corporations to produce biofuels. The novel concept of the closed-loop system is very achievable based on experience of existing waste management agencies.
For instance, the Indian government launched the Swachh Bharat mission, which translates to Clean India, aiming to accelerate universal sanitation coverage. Additionally, the Indian Renewable Energy Development Agency have partnered with organizations such as Ankur and Systema Bio to implement waste handling facilities. By creating a relationship with the utility companies, GeoBlue would benefit residents and may generate profit. This revenue could expand adoption of the GeoBlue water closet by providing loans to residents. If implemented in only a few thousand households, the price of purchase and maintenance for each GeoBlue water closet could even be halved.
However, the microbial desalination cell technology is not a silver bullet. The substrates used in microbial desalination cells based on sewage are more complex than acetates. Biokinetic efficiency is therefore unknown. Furthermore, due to the relatively high cost, Microbial desalination systems have been limited to pilot-scale applications. The most notable deployment of this technology was in Glastonbury, a context very different to Dharavi. Moreover, more material research is needed to replace some of the highly specialized components in the microbial desalination cells. The ion exchange membranes in particular are the most sensitive part of the system and would also constitute the greatest bottleneck in the supply chain. Analyzing prototypes with emerging membrane technology may therefore be the answer to a more economical microbial desalination cell design.
To summarize, GeoBlue offers a circular economy solution to water and sanitation issues for the residents of Dharavi. The closed-loop system integrates responsible use of waste while the profits benefit the community.
GeoBlue, a sustainable sanitation solution.
All right, thank you, HBBE. Do we have questions from the judges? All right, Beth, jumped right on.
Hello, I loved your presentation. I think it's really compelling and super interesting. I wanted to ask if you had the opportunity to iterate with your NGO partners. Were you able to take your design back to them and get their feedback throughout your process? Yeah.
So yes, very first time when we designed this project actually was not portable. It was a built-in system, a traditional toilet, and then we showed it to an NGO. And a big feedback we got, which we implemented throughout the project, was that space limitation is far more of a problem that we thought of, that we hadn't thought of. We tried to limit space, and then we talked about what is the best way we can approach this solution. And the portability was the key factor that came from it. And when I referred this back as an idea to the NGOs, they really like this idea, because not only is portability important because of the compact nature, but also it's also not traditional houses. There's symmetry, and you know, it's easy to put things in different places, but not in informal settlements. And another thing that we wanted to consider is cultural nuances. And some people are still resistant to having a toilet at their homes, or going to the toilet at their homes, which is a cultural thing that has been going on. So we wanted to make sure that okay, the components are removable and people can take it to the place where they find most convenient and suitable. So that's the key thing that to take away to answer the question.
Wonderful. Do you have any other questions? Yes, Zoe, please. Okay.
Hi. So I guess leading on from that one is how is it transported? Just thinking of weight, I'm thinking of different kinds of things, and you know, how also would you get in contact? Was it via the NGOs that you're getting in contact with the people who are already doing similar roles within this?
Yes, so Swachh Bharat is a government organization, so I think we would go directly to them and see how much they can help us. In terms of answering the question, I'll answer a bit of it and I'll throw it to my colleague, Florian. In terms of moving it, I think he's going to be the person who's going to be best answering it, so I'll do it with the NGO side. And the other NGOs that we talk to is Dharavi Diaries that aim to progress and teach STEM to students living in Dharavi and people living in Dharavi. And they were very keen on implementing ideas, and we were and the previous development have been apps. So what we wanted to try do is integrate something where we have a app development through the community, and maybe we can get some resources or funding from that. And it also integrates the community, because we want to integrate the community as much as possible. We don't want to come in and you know, bulldoze the community, because that's not appropriate. That's just not right. In terms of other people, I think Enactus, specifically their Palash project, actually deals with water waste from so in India, what we do is we when we pray, every single religion, they have an offering in terms of flowers. So these flowers are often gone into water waste systems and are a form of pollutant. So they figured out a way and have people in contacts where they are willing to, I think they have a dye system or something like that, where they're able to use these flowers and have a responsible wastewater management. So they are very keen to work with us as well in this project. But yes, I think it would be a government-led as well as an NGO-led, and the government would hopefully give us projects that help us work with Iridis and I think Systema Bio and people like that we mentioned. And then Florian, you can answer the portability side.
Great, thank you.
So to answer the second part of your question about how we moved into place, we are imagining something like, for example, the way you sort of cart a fridge into position to have that level of mobility. The portability aspect of the design was considered primarily to make it easy to put it in a place where it's convenient. It's not necessarily that people should be able to move it throughout the way or throughout its use. It's the way we think about this sort of interaction design is definitely something that we need to take forward with this project. But essentially, the main is the components are removable to make sure that if it needs to be moved once there is water in it without the weight being very troublesome, because we calculated that it would weigh approximately 120 pounds once it's full, which is obviously very difficult to move. That being said, before it's filled with water and sort of wastewater starts to build up, the MDCs would weigh approximately 2 pounds, and the unit in its entirety approximately 20 pounds. So that seems like it would be doable, at least to put it in place. I hope that answers your question.
Yeah, no, I think that's great. I think that's definitely something that I would be thinking of.
Okay, we'll do one more quick question from Denise, and then we're going to break. Go ahead, Denise.
Hi. Well, I really appreciated the range of issues you tried to take on with this technology, both social and cultural. And so first, I want to say that it was very impressive. I'm somewhat familiar with the scenario in Dharavi and its infrastructure. And one of the things that I'm aware of is that the NGOs and the government tend to resist really transformative implementation because of the real estate values. There's an intent to kind of push Dharavi off its location so that they can develop there. And so one of the challenges that NGOs have had, and there's been a couple of design competitions, has been how do you revalue Dharavi and its infrastructure so that you can explain how it should stay where it is. And so I think your project has an opportunity to take that on, and I'd like to hear what you think about how you could frame that possibility.
Yeah, I think, yes, what you're saying about the conflict, and if that's the appropriate term, in terms of the residents and I guess the government, because it is an informal settlement, although Dharavi has a special status where it's a bit unclear about its status on the law and the cultural side. But yes, we chose Dharavi specifically because of these opportunities. And in terms of the value addition, I think the big point would be the sale of the waste to biofuel companies, which is and if this is able to generate a profit and able to, as you say, revamp the community, I think that is also something that's a bit different from traditional NGOs, I would say, which is just helping the community and not maybe building a proper infrastructure for them to be independent and having a profit loss system. And I think that would be something that's for sure in that we should look at. And also this can also be used as fertilizers It's also, the brine can also be used for concrete out and reduce greenhouse emissions from that sector. I think maybe Florian has something to add to that.
Yeah, sure. Thank you for that. What I'd like to add is that I think the main challenge for us would be to present this as an affordable solution that the government would also be willing to invest in. And it's a challenge, but also an opportunity, because it is a settlement where people have been for a very long time. So I think the way we could sort of morph this into that transition is by presenting it as a solution in the areas, specifically in Dharavi, that are officially recognized, and sort of slowly move into, I suppose, increasing land tenure based on this product with the government.
Also, I think this might be where we seek support from our NGO partners. I think Dharavi Diaries have something similar where they're helping the community by a community-led approach, and it's they've actually developed apps. Like the people have developed apps who've been working on it. So and they've won awards. They've won quite a lot of recognition. They've gotten in worldwide. So I think talking to them and recognizing what they've done and maybe reflecting those approaches, or getting the support from them, would also help us guide in that realm. Because again, we've only done limited. We only know limited knowledge because we haven't been able to go there, unfortunately. But yeah, so this is definitely something we would look at with our partners. But thank you. Yeah.
Thank you all. Good job, HVBE. If you all could turn your videos off. We're going to go into a 15-minute break now. We just finished our first session for the day. So we hope you'll all stick around for a little bit. We have some commercials from some of our supporters, as well as past student projects, just artists from the community, just a lot of spotlight. So I hope you all will stay for this, and we'll see you in 15 minutes.
Around 70% of Finland is covered by forests, making it one of the world's most forested countries. The forest industry here has thrived for centuries, and the proximity of nature to everyday life has created a deep cultural bond. Forests have helped people survive and evolve throughout time, providing countless resources at both the macro and micro scale. Finland's forests are not only cherished economically and recreationally, but also for research and education. Recent studies have shown biotechnological applications within the forest sector are a high priority in academia and industry alike, especially the utilization of side streams for bioenergy, biochemicals, and other food or pharmaceutical applications. Pine, spruce, and birch are the three major tree species found in Finnish forests, and the spruce tree has some particularly compelling properties. Similar to any tree, the spruce tree has layers of protection in the form of bark. Bark shields the inner systems of the tree against disease, animals, and insects with various chemical compounds. The type and amount of compounds are unique to each species. What makes spruce bark exceptional is its concentration of phenolic compounds within the inner bark portion of the tree. These compounds can be easily extracted and provide UV protective and antibacterial properties. The extract contains natural stilbens such as resveratrol. These compounds are strong blockers of UV radiation in the range of 200 to 350 nanometers, absorbing a large amount of the wavelengths most harmful to humans. Studies have shown these compounds to be comparable to commercial sunscreens in their UV absorptive capacity. The antibacterial properties result from a combination of several compounds, including stilbens and various resin acids. While no single compound explains the effect, the extract shows strong antimicrobial activity against a broad spectrum of bacteria. Currently, industrial wood processing involves removing bark and burning it for energy. With such valuable compounds going to waste, our team explored how to utilize this side stream in a more effective way. We asked ourselves, what if we could take the protective coating for trees and turn it into a protective coating for people? Spark Fabric utilizes microcapsule technology to embed spruce inner bark extract into man-made cellulose fibers, producing a protective fabric that is versatile, organic, and renewable. This embedding of spruce inner bark extract enables the creation of lightweight and breathable UV protective clothing for warm climates, shielding its user from harmful rays as well as preserving vibrant colors and fiber integrity. The fabric's antibacterial properties minimize body odor and allow for longer periods of use between wash cycles. These fabrics help resist pathogens, providing a more hygienic garment and responding to a growing desire for personal protection in public environments. Because bark is removed and burned as part of current industrial processing, the sourcing of spruce inner bark fits nicely into the existing system. The bark is collected from trees prior to storage in order to preserve the active compounds. Ethanol is added to the bark, mixing with its existing water content. The mixture is then heated and pressed to remove the liquid, leaving the entirety of the bark solids to be used for energy production. The ethanol is then recovered and recycled. The extract is then microencapsulated using the simple coacervation technique, with starch as the wall polymer. These microcapsules are attached to the fabric through a bath containing a binding agent and a catalyst. The walls of the microcapsules break down based on acidity, heat, moisture, and other factors, enabling a slow release of the extract over time. In this rapidly changing, highly populated world, consideration of a product's life cycle from beginning to end is vitally important. Spark fabrics are designed using renewable resources and industrial side streams. The extract is 100% natural, and attaching the microcapsules to man-made cellulose fibers creates a biodegradable fabric that is made entirely from trees. The forest is precious. In our product, it provides inspiration, chemical compounds, and composition of the fabric itself. Our mission is to gather and utilize these resources in a way that protects the user as well as the environment it is sourced from, ensuring the health and longevity of these forests. For some extra protection, Spark, Shield of Spruce.
Hi, I'm Dan.
I'm Vina. I'm Alex.
And I'm Emma, and we're the team behind Biodesign Challenge.
We want your help to publish our first ever book, Biodesign Challenge, a retrospective.
BDC is an international education program and competition that's shaping the first generation of biodesigners. We pair high school and university students with artists, designers, and scientists to envision, create, and critique transformational applications in biotechnology. Our projects have gone on to show in museums and galleries around the world, and many have served as inspiration for new companies.
The book will be a full-color celebration of work produced by the BDC community over the last 5 years. It will feature 28 projects that bridge art, design, and biotechnology. Not only will it include essays by our alumni, but perspectives from eminent practitioners in the field.
Newcomers will find a primer on biodesign and how it's shaping the future of sustainability. For those already familiar, the book will offer insights from thought leaders, including biologist Paul Fremont, curator William Myers, and many others. It'll also include a foreword by Paula Antonelli, Senior Curator of Architecture and Design at MoMA.
BDC has collaborated with organizations including Science Sandbox, the National Endowment for the Arts, the Parsons School of Design, and the Museum of Modern Art, where we hold our annual summit. We're publishing the book in partnership with the University Science Center in Philadelphia.
So, if you're interested in learning more about innovative and fascinating topics, or if you just want to be awesome and support the next generation of biodesigners, then this book is for you. Every pledge, no matter how big or small, helps bring us closer to our goal. Thank you for your support. We can't wait to share the retrospective with you.
What if we could grow everything? Biology can. It's responsible for everything from the tiniest bacteria to the tallest tree. And at Ginkgo Bioworks, we believe that we can learn from nature to improve our own technologies and make everything, from fragrances to food ingredients to pharmaceuticals. The instructions are already out there in the A's, C's, T's, and G's that make up DNA. It's all biological code. And not only can we read that code, as synthetic biologists, we can write with it to program cells the way people program computers. So what does this look like in action? At Ginkgo, we work with companies and organizations in all industries who want to grow their products with biology. We see living organisms as the factories that can assemble those products, and our teams design, build, and optimize those factories to grow more stuff. Let me walk you through a product's journey through our foundry. Say you want to make a molecule, like an antibiotic. Our organism engineers start by looking at nature to understand the enzyme pathways that produce the antibiotics we use every day, and perhaps discover new antibiotics that we don't yet know. They work with our computational DNA design team and generate libraries of thousands of possible pathways. Those enzymes are of course going to need an organism to work in. Organism engineers select and domesticate the right strain for the job, whether it's yeast, bacteria, or a plant or animal cell. The next step is to compile our digital code into biological reality. People, robots, and software work together in our foundries to print and assemble the pieces of DNA and transfer them into cells. Automation enables us to scale every step of that process, making it possible to do exponentially more every year. Now that we have thousands of those engineered organisms, it's time to see what our potential antibiotic factories can do and find out which one works best. We want to know everything. What molecules are the cells making? How happy are they making it? Which factories work, which ones don't, and which ones can we improve? To answer all those questions, we use a range of analytic tools, high-throughput assays, and omics capabilities to characterize the organisms and enzymes. When we've optimized the pathway for producing our molecule, we use our automated fermentation systems to design the process that we can translate into pilot and commercial scale production. We capture all this data about each gene, enzyme, and organism so that we can find the best antibiotic factory. But all that work and knowledge also feeds back into our code base, our biological portfolio with millions of sequences that help us better understand how nature works and continually improve our abilities to engineer biology, regardless of what product we're making. What if we could grow everything? This question drives us in all the projects we take on. We're working with our partners to produce nitrogen fertilizer, more sustainable foods, and living medicines that treat disease right in your gut. We've even resurrected the smell of an extinct flower. We're equipped for both the questions we can anticipate and the challenges we can't. When COVID-19 hit, we mobilized our platform to fight it. We're supporting organizations in developing antibody therapeutics, optimizing vaccine manufacturing, sequencing viral RNA, and scaling testing. We've adapted our tools and facilities to create Concentric by Ginkgo, which offers large-scale testing to communities. So, can we grow everything? Not yet. But as we grow the future of synthetic biology, the most important questions to us at Ginkgo are, what's next? And what if?
Contaminated soils, communities saddled with lack of employment. These are the legacies left behind by the decline of the mining industry in South Wales. However, this contaminated soil can now be used for the production of something called a quantum dot, with the help from a very familiar garden friend. So, what exactly is a quantum dot? It is an incredibly small semiconductive particle. It emits different coloured light in different sizes when excited by light or electricity. They have been used in a range of different applications such as biological imaging, improved LED screens and solar cells. The industry is set to be worth over $11 billion by 2026. In 2013, researchers at King's College found that they can be biosynthesized using the earthworm through a process called mutual antagonism. When earthworms eat soils containing metals, they produce enzymes called metallothionein in its gut. The metallothionein grabs hold of the metals and stores it away in special cavities inside the cells. It reacts with another toxic element to make a safer compound. This is the quantum dot. Professor Mark Green of King's College explained,
"Extracting a quantum dot made in a worm is a cheaper, more sustainable process than making quantum dots in the laboratory."
Quantum Industries is one company striving to exploit this phenomenon. Working with a disused coal mine, they have biologically engineered a giant hybrid earthworm optimised for high-yield production of quantum dots. These earthworms are hatched in secure wormeries inside the mine. To attract the wormer runs a light electric current into the soil. The worm is then tickled to release the fluid containing the dots. This mine uses its cadmium and selenium contamination to create a cadmium selenide quantum dot. The BBC interviewed Margaret Howell, CEO of Quantum Industries.
Though we intend to sell quantum dots on as a green and cheaper alternative, our real aim is to generate clean energy using the quantum dots in our solar flags.
Quantum Industries are now fabricating innovative solar flags using spray-on solar cell technology. The flags are raised around the mine, powering itself and the nearby community. Quantum Industries hopes this would re-establish mines as a source of energy, bioremediating the coal industry's pollution and revitalising the industry in the area. Olivia Bargman pollution and revitalising the industry in the area. Olivia Bargman, BBC News, Glenavon.
Jeff, are we live? Jeff?
Bina, it looks like you are.
Am I live?
Yeah.
Okay, well, we're gonna go for it. Welcome back, everybody. We're going to go right into our next session. Thank you for joining us today. If you're just joining us, we are starting with our first high school for the day, Atarraya UniAndes, and we will show the video in just 1 minute. Thank you.
In Colombia's rural areas, access to basic services such as electricity, safe drinking water, and gas are limited. Because of this, 3 out of 10 people do not have access to hot water, causing negative impacts on physical and emotional health of families. Usually, Colombian families heat water through electrical heating, gas, or firewood burning. However, each of these practices may have negative implications. First, electric heating represents a constant fire risk. Also, as mentioned before, many families have no access to electricity, making it impossible to use this method. Second, natural gas heating is difficult to acquire due to high prices and lack of infrastructure in rural and suburban areas. Third, firewood burning produces fumes that put the physical health of families at risk. This method is also very slow and inefficient process. This is everyday life in the village of San Antonio de Palmito in the Caribbean region of Colombia, where 630 families of an indigenous community have no access to gas and drinkable water. This problem is also present in low-income families in Colombia's capital, where there is a lack of natural gas heating. Both of these contexts were explored and analyzed by our group, given that we were in different regions of the country due to the pandemic. Energy Plus is a system that provides a sustainable source of energy to access basic services in vulnerable communities around the world. Energy Plus is a project in which solar thermal energy, along with biogas, is used to improve the life quality of people who live in rural and suburban areas, people who have no access to basic energy sources such as electricity and gas. The system works by combining solar thermal energy and biogas. Biogas is produced from food and agricultural waste in a biodigester owned by the community, where a fermentation process is generated by methanogenic bacteria. Energy Plus presents a cost-effective solution for low-income families. We found that to heat with natural gas around 4.5 cups of water, the cost is around $6, while with electricity it goes up to $13. But thanks to Energy Plus, users could reduce their expenses by building the system with recycled materials, allowing to produce biogas with organic waste or animal manure collected from homes and farms. The production of biogas is not a new technology. However, what is innovative in our proposal is integrating different technologies in a life quality changing system, giving vulnerable communities access to basic energy sources at a low price, and collaborating in its construction and maintenance. Energy Plus responded to the Sustainable Development Goals as climate action, clean energy, good health, and well-being. To achieve this, we analyzed how gas production varies in different geographical areas of our country. Some of the members of the team were in Sincelejo, near the north coast of Colombia, and others were in Bogotá. By experimenting in both locations, we found that when environmental temperatures are higher, more biogas is produced. In areas with temperatures between 25 and 34 centigrade, it takes 5 days for a 140-liter tank to be filled with biogas, whereas in areas with temperatures between 0 and 15 centigrade, it's about 20 to 30 days to fill a tank with the same size with organic waste or animal manure. Biogas is produced and collected in this biodigester. 50% of the tank is filled with organic waste and animal manure and water, leaving the other 50% empty in order to allow the accumulation of gas. Then the gas is transformed in 2 pipes, one for gas and the other for heating water. Energy Plus also designed a heating water system that allows users to collect rainwater or water from a local pipeline. Inside the collection tank, water can take 2 different paths. The first one leads to a chamber made up from recycled PET bottles, which captures solar thermal energy. The first chamber connects to a water purification filter to make it drinkable. The second leads to a pipe that takes water into a heater that uses the gas collected from the biodigester. Since our prototype uses methane gas and water, it may have some handling risks. However, incidents and damage can be prevented by following safety instructions and guidelines. For this matter, a maintenance service will be provided through a network by trained members of the community. In addition, Energy Plus has an instruction booklet that guides the community in the process of building the device. Since we want this system to reach rural areas, the instruction booklet will be available in educational technical institutions, community centers, and other strategic areas can access this biotechnology for their benefit. With this system, we want to give a solution to our families, neighborhoods, country, and in the near future to different families around the world. Energy Plus means the possibility of changing positively our families' physical and mental well-being.
Energy Plus empezó gracias a unas clases que teníamos con el profe José Luna. Empezó con un proyecto de una bicicleta para darle energía a estas personas de bajos recursos, pero gracias a la pandemia debimos cambiar el proyecto y ahora con un mecanismo especial vamos a darle agua caliente a estas personas de bajos recursos.
Este proyecto no solo tiene repercusiones positivas dentro de las comunidades rurales y urbanas de Colombia, sino que logró la unión de un equipo de estudiantes diversos enfrentándose a un mundo de retos y distancia por la pandemia. Específicamente, la primera investigación se realizó en nuestro contexto Bosa en Bogotá y luego en Sincelejo, al norte del país.
Este proyecto se va a beneficiar en todas las familias de nuestro país que no tengan acceso a los servicios básicos como el agua, la luz y el gas.
En este biodigestor se recolectará el gas. Para ello se necesitará residuos de animales, cáscaras y agua al 80%. Luego el 20% de gas se acumulará en 2 pipetas, una para la cocina y otra para calentar el agua. El agua se recogerá del agua lluvia o de agua de acueducto. Para calentar el agua sería en una cámara y para generar el fuego sería en un generador que genera 40 kilovatios. 2 kilovatios para calentar el agua y 38 para distribuir por toda la casa. Luego esa agua calentada se va a ir se va a almacenar en un tanque y estará lista para distribuirse por toda la casa.
Okay, Thank you, Atarraya. We'll go right into the Q&A. Do we have any questions from the judges? They're just so taken aback and excited by your project. Oh, they all came at once. Okay, let's start with Denise, please. Go ahead.
Hi. I'd like to hear a little more about how you engaged with the community and how your communication, your graphic communication was used with the students and with the community members. How did you work together? Was it all spoken or did you use graphic tools?
La pregunta es, ¿cómo fue su involucramiento con la comunidad? ¿Ustedes le mostraron, digamos, los modelos gráficos que hicieron o todo fue verbal, esa aproximación con la comunidad?
Buenas tardes, bueno, todo fue verbal, ya que primero que todo el proyecto se empezó con nuestra comunidad y primero empezamos fue con un formulario para que ellos lo llenaran y como estábamos en medio de la pandemia, todo tocó hacerlo verbal. No pudimos, hicimos claro el prototipo, pero todo fue por plataformas.
Gracias.
So the answer was that they did everything through communications, verbal communication, because due to the pandemics, it was really hard for them to go to certain places. They started with the survey they gave person where they first identified that hot water was an issue that people in Bogota, because they asked within their communities in Bogota, whether they didn't know that this was something people didn't have access to. So they started doing surveys to identify that there was a need they had to work on.
We will go to Zoe next.
Hola, buenas. Hi, everyone. To ask my question in English or Spanish, I go for it in English. So which kind of materials or agricultural waste were you collecting? ¿Qué tipo de materiales, agriculturas has juzgado?
¿Cuáles fueron los materiales, Sara, que utilizaron en el contexto agrícola para su biodigestor?
Nuestro primer prototipo fue con un balde pequeño y con un tubo para mirar y con una llave para mirar a ver si el biogás funcionaba. Todos hicimos lo mismo en la casa. La verdad, no a todos nos funcionó. Eso fue experimentar en casa. Ya después fuimos creciendo y fue ampliando nuestra mentalidad. Ya después le agregamos el estiércol de vaca para el campo. Ya después se le agregó varias cosas y también estamos como mentalizados a un futuro seguirle agregando cosas. Mejor dicho, nuestra mentalidad está súper abierta, hemos pensado en cámaras subterráneas, pero pues básicamente fue todo con cosas de la casa, lo que encontráramos hacer nuestro biodigestor.
So they first tried these, each student tried it at home with things they found at home. Then they also used cow poop. For some students it worked, for other students it didn't work, but they say they have this open-minded philosophy of continuing trying things, wastes they can find at home to try to get the most efficient biodigester and produce the most gas possible.
We'll do one last question from Margaret. Margaret, you're muted.
Sorry, I apologize. I was just commending you on your project and wonderful presentation, so you missed that. But I want to ask a little more about this field research component, because it seems like I really like the fact that you've chosen a specific community that's important to you and that you generated surveys. So you got a lot of input right at the get-go, at the beginning of your design. I think that's a wonderful way of approaching it. Have you gotten to the part, you may not have yet, there's a lot that you've done already, but what's the next step? Have you gotten to the prototype and gotten, how do you imagine getting feedback and getting this actually incorporated into the lives of people that you're looking to serve? You talked about training members of the community, but part of that process, right, and getting the prototype, seeing what works, what doesn't, how do you imagine that happening, or have you already done some of that?
Primero los felicitó, qué gran presentación y qué gran proyecto. Y la pregunta es, ¿qué tanto han avanzado con su prototipo y qué tanto han hecho con la comunidad? Si ya se han aproximado a la comunidad, ustedes mencionaban que iban a llegar a la comunidad para que ellos sean capaces de construir este prototipo. ¿Qué tanto han hecho? Y si todavía no lo han hecho, ¿cómo piensan aproximarse a la comunidad para que esto sea posible?
Bueno, sí lo hemos hecho, ya hemos practicado con algunas familias. De hecho, estamos invitados para dentro de unos meses ir a un colegio acá de Bogotá, en la parte del norte, para poder hacer el biogestor en un colegio para estos chicos. También hemos ayudado a personas no solamente de Bogotá, sino también hemos hecho el prototipo fuera de Bogotá con otras familias, para así poder llegar y que nos conozcan. También hemos querido hacer una cuenta de Energy Más en redes sociales para que varias personas puedan también conocernos y que la información pueda restringirse a través de varias personas.
So they have already tried their prototypes with several families, and that they are actually invited in a couple of months. In July, this she didn't say, but in July, classes will start in Colombia again, in real, like at the classroom. So they are invited to go in a few months to a school in the north of Bogota, so that students in the school can learn how to make a biodigester and implement it in their school, and that they want to do some social media so that people can become aware of what is Energy Plus, and where they find interest, help these communities to build their own biodigester so that they can use it in their context based on the ways they have.
Excellent. Thank you. Thank you for that answer.
Okay, we are out of time. So, if the judges have additional questions, the students will be here for the gallery show as well. So I hope you all will join us for that. We're going to move on to the next team. Thank you again, Atarraya UniAndes. You guys did wonderfully. We're going to move on to the Design Village in India.
In 2020 January, people from across the world started facing the effects of the pandemic. In India, people started sharing all types of necessities with those who were in need, oil being one of the most crucial. From waking up in the morning, one's interaction with oil begins. It is not just essential for cooking, but the Indian culture is embedded with various uses of oil through various stages of life and across all age groups. On basis of different packaging material, the interaction also differs. Edible oil is a source of dietary fat, one of the three major classes of food. It plays an essential role in the body, satisfying nutritional needs, growth, and is necessary for proper functioning of the brain and nerve system. Starting with cooking breakfast for oneself and family, to oiling our hair, massaging the baby, applying it as a moisturizing agent on the body, used in home remedies to cure small cuts and bruises, and also for various other purposes. Our everyday life is filled with interaction with edible oil in one way or the other. This makes India the largest consumer of edible oil. But what happens to the packaging after its consumption? Most of the edible oil packaging is made of LDPE, PET bottles, and tin that are either burned or dumped in the landfills. The plastic packaging in landfills further disintegrates into microplastics and ends up in water bodies, affecting the whole ecosystem. Edible oil and its packaging are made for the consumption of the human race. Looking at the entire system, one can easily understand the only stakeholder that benefits from the production are humans. How can we introduce inclusive industrialization, which is ethical, responsive, and beings involved in the system can benefit from it? We introduce you to SPOIL, that stands for Sustainable Packaging for Oil, that focuses on production, consumption, and externalities, which aims to benefit all stakeholders involved in the system. Why SPOIL? A play on the notion of packaging, Spoil is provocative and questions the convention of edible oil industry. This design proposal rethinks the nature of both edible oil and its packaging. Let's delve into the existing edible oil industry. Soybean oil seed has been taken as an example here to show the production process of oil. The process begins by the sowing of seed into the soil, which further turns into a sapling to a grown plant with flowers. The flowers further develop into fruit, which contains soybean oil seeds. These seeds, after drying, are harvested and sent to the oil industries. There they go through cleaning and drying in order to remove the husk. They are further converted into flakes, which then go for extraction through either mechanical or solvent extraction machines. From this, the byproduct obtained is called oil cake. Oil cakes are further used for feeding cattle. The oil which is extracted goes to the refineries. There it goes through 4 processes, which are degumming, neutralization, bleaching, and deodorization. From these processes, we get byproducts which are lecithin, free fatty acids, and acid oil. After the refining process, oil that are rich in polysaturated fatty acids are prone to oxidation and go through a certain process called winterization that helps separate saturated and unsaturated fatty acids. The byproduct obtained here is stearin. Stearin, being rich in saturated fatty acid, is solid at room temperature and less prone to oxidation. Stearin is used in baking industry as an alternative for cocoa butter. We found some potential in stearin and started experimenting with it. A human body needs 22 grams of saturated and 44 grams of unsaturated fatty acid in a 2000 calorie diet per day. The Spoil pellet is designed by keeping this in mind. Each pellet contains 4.75 ml fatty acid, 1.58 ml of saturated, and 3.17 ml of unsaturated fatty acid. Stearin acts like a protective layer for the unsaturated fatty acid, making it less prone to oxidation. The form of the pellet is spherocylinder. The reason for choosing this form was its less volume to surface area ratio, which ensures that the consumption of saturated fatty acid will be lower than that of unsaturated fatty acids. The form is also associated with medicine, hence creating an image in the mind of the user to be conscious about its consumption. In order to protect the pellets from external hazards, secondary packaging is introduced. During the process of extraction, oil cake, which is a byproduct, is obtained. Oil cake is rich in antioxidants and proteins, which is great for protecting the capsule from getting oxidized. We try to develop it into a potential biomaterial for packaging. In order to make the material flexible for packaging, pectin from lemon peels and glycerol were added. The mechanism of the packaging is designed in a way that only 2 capsules are dispensed at a time, which will make the user conscious about their consumption. 1 pellet is equal to 1 teaspoon of oil. The packaging contains 500 ml of oil, which is 105 pellets. The form is decided on the basis of familiarity and efficient stackability of the pellets. The form can be easily stacked in one's kitchen without using up a lot of space, and it fits perfectly in the hand of the user. The secondary packaging is biodegradable, and after its usage further goes into the soil to act as a fertilizer for the soil due to its high nitrogen content. This packaging and the capsules together comprise Spoil. Spoil is an experience, a rather new one for using edible oil, a recomposition of existing process in an eco-centric manner, keeping the cultural relationship with oil intact.
Okay, welcome to the Design Village. Thank you, students, for that presentation. We will go right into the Q&A. So whenever you're ready, judges. All right, Ben, and then we'll do Chaz.
Sure. Yeah, thank you. That was a wonderful presentation, and great insight into the needs in your community. I was wondering, in terms of that impact, let's say you created this and it was adapted or adopted, by your community. What kind of impact would it have? What kind of waste product would it save? I don't know if you've quantified that in some way, or envisioned, how would it impact your community?
Hi, that is a great question. Thank you for that. I would like to answer it. So, because like during the survey done in India during the time of 2017 and 18, it was found that one person, like per person, India consumes around 14 kg of oil per year, which is more than actually required for a human body. So the main point of spoil is actually to target the consciousness of consumption in India. So we want to actually explain to people that, you need to be conscious. So when we are using a liquid, what happens is we are not able to measure it as such. We pour it and maybe sometimes we use more than needed. So it will actually make the user conscious that, okay, I have used 2 pellets or I have used 3 pellets and it's, 5 ml of oil or 1 teaspoon of oil. So like that. And also it will keep the cultural aspect that is, attached to oil intact. Because like, for example, if you're oiling your hair, you actually need to heat it before you make it you actually heat the oil a little so that it, gives all the nutrition to your scalp. So yeah.
All right, we'll move on to Chaz. Yeah, go ahead.
Hi, I thought that was a really great presentation. I really enjoyed it. And I actually had 2 quick questions. One, how would the cost compare to traditional methods? I was just curious about that. And the second question is, you talked about some of the cultural components. Would you be able to use these spoil capsules for oiling the hair, or would you need to heat it to access the liquid oil?
So hi, so we designed this system on an existing system of oil production. So anyway, the main product like styrene and other types are already existing in the system to produce various alternatives for cocoa butter and oil. So we are actually utilizing those byproducts and then making capsules. So here I can show you how the prototype is. So this is the spoil capsule. So the outer layer is a saturated fatty acid, and then it is filled with unsaturated fatty acids. So we literally made like that, and once after consumption, once after consumption you can literally even the packaging for the main material for the packaging was oil cake. So even that is also a byproduct that is currently being used as a fertilizer and also as a cattle feed. So we are using the fertilizer portion of it to make the packaging, and once after consumption, it again goes back to the same system as a fertilizer. And answering your second question, like we said, since anyways when we apply massage oil, we used to heat it. So spoil can be also heated at the same time and applied. So we are still keeping the cultural things in the same way. Only thing that we are intervening is the mindful consumption of the oil. Thank you.
Also, I would like to add to Arshad's point, because we are using the same ingredients and the byproducts from the same system, the other the consumption part of it and everything, and the spending of money on the resources, getting new resources, setting up a new industry, and also saving on the energy consumption of a lot of things. So like for transportation, for example. So all those things, we are not actually spending on that. It's the same industry. So yeah.
Great. One last question from Magnolia.
I think my question is sort of related to all of the, I think all of our questions relate to ideas of scale and how this gets implemented. And I guess one last little bit that you started to touch on is just thinking about the sustainability of it in terms of how much energy does it cost to make this sort of new packaging, which then biodegrades, which is great, but just in terms of how much energy does it take to transform that into the packaging?
So like currently, because India is going through a really rough time because of the COVID-19. So we actually did all the experiments at home from different places, because we are, situated in different places in India. So we actually did all the experiments, and the methods that we used, we have to still, work on that, because we don't know if on a larger scale production, the same sort of methods are going to be used. So we still need to, figure the production part of it, that what machineries are you going to use, what tools are going to use. So we still need to figure out that.
Wonderful. Oh, good.
I would like to show the material that has been developed at home. So I hope you can see this material. So it's flexible, it's strong, and it's made from the oil cake, which is a byproduct coming from the same industry.
Amazing. So you all have next steps too. That's wonderful. Okay. We are going to move on. Thank you again to the Design Village. Wonderful job, y'all.
Thank you.
Take care. Okay, we're going to move on to the Applied Science University in Jordan.
Jordan endures from a serious water shortage issue. The country is one of the 4 driest within the world. Only 4% of Jordan land is arable and less than 1% is forest and woodland. Jordan is among the poorest nations within the world on the premise of per capita water accessibility, with as it were 147 cubic meters per individuals per year in 2010. Renewable water assets are less than 130 cubic meters per individual per year. In case supply remains consistent, per capita household utilization is anticipated to drop to 90 cubic meters per person per year by 2025. As for a study by Stanford News, decreasing water supplies and a developing population will divide per capita water utilized in Jordan by the conclusion of the century. The World Health Organization estimates half of humanity may live in water-stressed areas by 2025, and the United Nations anticipate water scarcity could displace 700 million people by 2030. Demand for water has climbed to a great extent since of population growth punctuated by waves of refugees, counting more than 1 million Syrian refugees within the past decade. But the future does not have to look so dark.
Hello, this is Rupa Jadallah, the Dean of Art and Design faculty. As the team instructor, I'm delighted to say that our students had an amazing experience participating in Biodesign Challenge, discovering and learning how bridging biotechnology, art and design can bring solutions to our lives. This is our first participation in Biodesign, and despite all the difficulties we have gone through during COVID-19 lockdown and being unable to access labs and materials for the experiments, but our students did an excellent job. I want to extend my gratitude to people behind Biodesign Educational Program for giving us the opportunity to be part of this challenge, as we are here at the Faculty of Art and Design very keen to add the Biodesign as a mandatory module to teach to our students, so we can prepare a future designers incorporating biotech and design. And we hope to keep taking part in this amazing informative challenge.
My name is Mohammed Al-Najjar. I'm Associate Professor of Microbiology. I was so pleased when Dr. Ruba and the students approached me concerning the Biodesign competition. So they brought the idea of reusing the grey water that is produced or generated in the College of Arts, and they wanted to grow algae on them so that they have 2 things. The first thing is to purify the water as much as possible to be used to water plants, and the second thing will end up with biomass that can be used for biofuel. Actually, I was so happy to join them and to guide them with the biology part because it's my field. So the idea was to grow the algae under favorable conditions so that they can utilize the nutrients that are present in the gray water so that the water quality will improve. And this improvement will let us use the water to water the plants. And at the end of the experiment or with the time, the biomass can be collected and can be used to generate biofuel that can again be used for the college for heating in winter or for other purposes.
My name is Hadil Hani. I study interior design at the Applied Science University. We came up with this idea as a group because we wanted to help with the water problem here in Jordan. We did so many studies and researches because we wanted to use that water for other things like watering plants. And hopefully, we want to implement this idea beyond our university to other places here in Amman.
My name is Qais. I study interior design at ASU. I joined this project because I personally believe it would be nice to see this project implemented on my college and on my city in the future.
I am Sada Khalil. I study interior design at the Applied Science University. After the studies we have made, my friend and I, Qais, have made some sketches in 2D and 3D to show the idea of our design in reality.
As we know, Jordan is suffering from lack of water and shortage of water. So I think it's very useful to go through this kind of project to reserve water for agricultural uses and other purposes. Yes, I think it is a very good idea.
I think the idea is great. It's great for the environment and it's something new for the community here as well. As for the design, I think it's not something you see every day, especially here in Jordan and stuff, so I think it's a good start. It's different, it's creative, and I'm quite excited to see the finished project come to reality.
Simply said, the country that we're in, Jordan especially and stuff, has multiple droughts. It doesn't rain too often in the winter. It's like it already is known to be a desert land as it is from other countries as well outside. So if we do manage to actually reuse water to to water the plants and grow more plants, and it basically becomes more eco-friendly, especially with the pollution that we have, and it just works a lot better basically. So yes, I do think it's a very good idea, and it would be really good to have it, especially in a country like Jordan.
All right, I'm not hearing from the tech team, but I'm going to assume that we're live. Let's go. Thank you, students. That was a wonderful video. Let's go straight into Denise.
Hi, thank you for that. Could you just describe step by step what the actual proposal is? Like how we see that there's the pipes on the facade of the building and the chamber for the algae. Can you just tell us how it works quickly?
Okay, I'm gonna explain. Hello, everyone. First of all, we have so many plastic wastes in our college Faculty of Arts and Design. We contacted a factory so we can exchange these plastic wastes, such as plastic bottles and bags, and we're gonna exchange them with pipes. These pipes are the main idea of the design. The idea is to filter the gray water we used at our faculty. We're going to plant a type of bacteria with algae, blue-green algae, cyanobacteria. We're going to plant it in these tubes. So while the water goes through these pipes, it's going to be filterized. That's just a general explanation. Is that good, or do I need to say? Yeah.
Thank you.
You're welcome. You're welcome.
All right, Ben, go ahead.
Yeah, I like the I like the concept of integrating these into the design of the building itself, where you're not only treating the water or recycling the water, but incorporating the design of the whole process.
We are interior design students after all.
Yep. No, that's great. So I wonder, just in terms of the impact that this can make, clearly you're thinking about your building and your school, but can this be translated into other buildings on campus or anywhere else?
Yes, since we thought about the whole experiment and we made a prototype, it's very applicable on other buildings. It can be easily implemented on the rest of our university, so we can contact other deans and other faculties, and it can be used on other buildings. But we also were thinking about implementing it outside our university on other buildings, and it's very applicable since it's a very simple project. We can just recycle the plastic, put the filter, put the tubes, and it's very applicable on other areas, not just our faculty or our buildings in the university.
Great. Chaz, would you like to go?
Hi, team. I really enjoyed your presentation. Thank you. My question is, with the treated water, are there any limitations of that usage?
Yes. Now this water can't be used for drinking. It will only be used for watering the plants, as we manage to use other chemicals and stuff for it not to be very harmful to the plants, but it's not very purified to the state where we can drink it, as we mainly want to use it for watering the plants.
Thank you.
Oh, you're welcome.
All right, it looks like we have no further questions. So thank you so much, students. Wonderful job. We will see you all very soon at the gallery show.
Yeah, you're welcome.
Take care. Let's move on to our last team, College for Creative Studies.
Welcome to Reform, Reformation of Thermoforming Materials. Since 1964, vacuum forming has become one of the most common methods of processing plastic materials. The process involves heating a plastic sheet until soft and then draping it over a mold. A vacuum is applied, forming the sheet onto the mold. Once cooled, the thermoformed sheet can be removed. Vacuum-formed products are all around us and play a major part in our daily lives, from yogurt cups to hot tubs. Many consumer packaged goods, or CPG, utilize vacuum-formed materials for a very limited existence. Although they serve a temporary function, the materials used in the process, such as ABS, polystyrene, PVC, polycarbonate, and polypropylene, have lasting effects on the environment. Because of this, 30 states in the U.S. currently have some form of legislation regarding banning commonly thermoformed plastics. These legislations have led companies to seek new and alternative material development in accordance to our global shift away from plastics. We spoke to Julie Reed, industrial designer at packaging solutions company DART, about how they are reacting to these shifts.
It is something that we are actively working on. We have entire departments allocated towards doing research and development.
So we have to question, if thermoformed materials in CPGs require a limited existence, why use materials with such permanence? To solve this problem with a circular mindset, we aligned ourselves with the UN 2030 Sustainable Development Goal number 12, which is to ensure sustainable consumption and production patterns. We created a list of criteria for our material. This introduced us to a field of industrial food byproducts, the materials left behind with no sustainable use case in their life cycle. Our search for byproducts led us down several avenues, from orange peels to eggshells and many more. We selected local byproducts, spent grains, and sugar beet molasses, based on the properties we discovered and the added sustainability factor of locality. In the United States, beer is the fourth most consumed beverage with 5.5 billion gallons produced each year. This consumption leaves approximately 223 million pounds of spent grain left over after the brewing process. Although spent grains have been stripped of sugars after the brewing process, they still contain polysaccharides. Polysaccharides are organic polymers composed of many disaccharides. Disaccharides are molecules composed of two simple sugars. Simple sugars are also known as monosaccharides. Spent grains are also largely composed of fiber and protein that can introduce additional structure to our biomaterial. The U.S. alone is expected to produce 35 million tons of sugar beets in 2021, while only yielding 5.2 million tons of sugar, leaving a tremendous amount of waste, including molasses as a byproduct. Sugar beet molasses contain the building blocks of polysaccharides, glucose and fructose, as well as disaccharides, sucrose. We hypothesized that we could create a strong yet elastic material by combining the properties of molasses and spent grains that can be applied to thermoforming processes. Then the fun began. We sourced our molasses from a sugar beet farm, Michigan Sugar Company, and our spent grains from Net Zero, an upcycling platform that captures and converts industrial food and beverage byproducts. We also included glycerol as a plasticizer and gelatin to provide flexibility. Our material development started by finely grinding our spent grains, then sifting it through a 190 micron filter to achieve a homogeneous texture and color by removing impurities. We formulated recipes with different ratios of ingredients to achieve the mechanical properties needed for the material. We started in the woodshop to fabricate frame molds for our materials to set up in and be vacuum form ready. In the lab, we measured out ratios of ingredients and cooked many samples in order to find a successful recipe. After pouring and leaving to cure for 72 hours, the samples were ready to take the ultimate test in the ProtoVac 100. The samples were heated and deemed ready when the top material began to sag and bubble. We pressed them over the forms, and some didn't make it back. But with our failures, we found successes. Introducing Reform, a thermoformable biopolymer that offers an alternative to petroleum-based polymers with applications for rapid prototyping and consumer packaged goods. Our material has a unique natural appearance and finish from the spent grains and molasses combined. It is uniquely elastic, making it suitable for thermoforming processes, and keeps its shape after the release of a mold. Compared to polystyrene, Reform is biodegradable, compostable, and free of the negative impacts its petroleum-based counterparts have. Reform is meant for biodegrading rather than recycling. Molasses and spent grains are both used in the agriculture industry for bioremediation of soil and water. And because they are byproducts, no new land use is needed. Our material can provide benefits to our environment rather than harm it. We sought out an expert in the field of design and spoke to industrial designer Patrick Schiavone about Reform's potential. He believed that it could be used for
any kind of product that has to come in a box that will in a completely biodegradable package. And again, I'm in love with the way it looks. It looks so natural.
In order to reach this potential, we are looking to have our material tested and discover its limits. Off of our conversation with Pat, we prototyped what packaging could look like and experimented with pattern formations. We shared our prototypes with Julie Reed from DART to get her initial insights.
this is super, super exciting. And frankly, it's amazing the quality of forming that you've been able to get with this. I'm shocked with it. What I think that your material has going for it is I see it and I see natural, but I see that it's also behaving the way I expect it to when it comes to thermoforming.
We believe Reform has the potential to reframe what thermoformed materials can be now and in the future.
All right. Thank you, CCS. We will go right into questions from the judges. All right, Ben, take it away.
Sure. Yeah, no, it's a wonderful presentation and application, and you've really given a lot of thought and experimentation in the lab to get there. So congratulations on that. I was wondering, when you think about plastics, obviously a lot of things that drive the use of plastics is cost. And I'm sure you've thought about this, in your product. What kind of cost comparisons have you done to think about how to get this kind of product adopted across the industry?
I'll take this question. Thanks, Ben. So compared to plastics, we do believe it'll be more expensive than the traditional plastics that we consume and use today. But then again, plastics have had years for it to be perfected and have its cost lowered to where it is today. And I believe this material probably just requires that amount of time and length. Speaking with Pat Schiavone, who was in our video, he did bring up the concept of using this as maybe an additional cost for, let's say, fast food, for example, to those who have the disposable income to invest in this product and continue the research and development in order to bring down the costs in the future.
Betsy, go ahead.
Hi there. Yes, this is a very interesting and thorough presentation, and seems like you really put a lot of work and thought into your processes. Aesthetics are really very important for adoption, so I'm interested and happy to see that you paid attention to the aesthetic component of your material. However, it's not a question. I just would like to hear a little bit more about the thought process that went into creating, and I like that you consulted with somebody who's an expert in the look of the product, but can you say a bit more about your process in terms of thinking about the aesthetics?
Well, as of our prototyping, we have achieved brown as the natural color of Reform, coming from the molasses and spent grains. We've really embraced this color as evidence of its origin, but we also understand that perhaps other colors could be desirable, and we're going to be looking into exploring different variations on the color brown that we can achieve.
All right. If you don't have anything else to add, we'll go one last question from Zoe.
Hi, team. Really well done on your project. I wondered what tests you had done in terms of, composting it, or, how it reacts to water and other things. What tests you've done there, if you could share that with us, please.
Yeah, perfect. So after showing this with the designer from Dark Container, prior to speaking to her, we had not conducted any proper tests that could give us quantifiable results. But after speaking with her, we are currently looking into prototyping with them and beginning professional material testing through our connections with the company Dark Container. Once we have those results, we'll look to improve things such as seepage, how does it react to water, acids, and even biodegradability. We just weren't sure how to professionally quantify those things other than saying that it may or may not be in our backyard and figuring out that time frame.
Okay, great. Thank you.
Amazing. Okay, we're gonna move forward. So thank you so much, CCS. Wonderful job. We'll see you guys later at the gallery. We're gonna now take another 15-minute break. So please stay tuned for some more commercials, and we'll be back very soon. Take care.
Hi, I'm Uyên. I grew up in Da Nang, Vietnam, where leather textile predominantly manufactured. Leather is widely used in many applications across the industries, but not only my country. Around the world, people are suffering from leather manufacturers' pollution. Leather tannings use toxic chemical agents. Some can be harmful for the human health and the environment. Moreover, false leather is often made from toxic polyurethane. It is plastic and at the end of the day would not biodegrade or break down. After working in the fashion industry here in New York for a few years, looking at the volumes of the textile materials never seen before, and the thread of microfiber, which is made from polyester, is entered into the rivers, lakes, and the ocean, and then appears to be consumed in food and drink. This triggered a deeper question for me, taking me back to the same one I have been dealing with in Vietnam. What if you can use waste to create a new generation of biomaterial that can solve the pollution problem? As I research, the food industry generates 6 million to 8 million metric tons of seafood cell waste every year. The seafood cell waste often contains a huge amount of chitin, a polysaccharide that can be biocompatibility, biodegradability, antimicrobial and antioxidant activities. Chitin and chitosan can be extracted by bacterial fermentation process. We produce almost 9.5 million tons of waste coffee ground every year, and most of it ends up in landfills, where every ton generated 14 tons of CO2. By combining this waste component, I created Tomtest leather-like biomaterial, which is dyed with eco-friendly natural ingredients like orchard, coffee, and charcoal. Tomtest would not only solve the textile leather pollution, but it would also move the seafood and coffee production into a better ecosystem platform. To me, Tomtest is not just a textile but actually a process. How can we start to look at the longer life cycle of the material, and how can we bring the environmental impact from where this industry stands currently? TomTest production carbon footprint require only 1.64 kilogram carbon dioxide equivalent per square meter. This is 100 times less than real leather and 15 times less than forced leather cost. Real leather, in contrast, use 17,000 liters of water to produce 1 kilogram of leather. It's 69 times more than TomTest biomaterial. One pair of real leather shoes can take up to 9,000 liters of water. Forced leather is 1,800 liters. However, with the current process, TomTest would only take 31 liters of water, with the added benefit of being able to recycle. When TomTest biomaterial is no longer fits its purpose, it can be easily recycled into new product. You can put TomTest into water, let it stay for 2 weeks until it dissolves, and then it can be casted again into the mold. TomTest is 100% biodegradable. It is also a natural fertilizer for plants. Today's system is big, and people don't really know what happens to the waste. If people could take a part of more local system and a smaller loop, I believe they will begin to be waste at our raw material. A local and closed loop system will provide a sense of honesty and transparency in the area that is normally hidden. As a textile biodesigner, my vision is seeks to reduce negative impact on the environment and improve the health and well-being of the people now and in the future. With TomTest, I can see that alternative systems of production and consumption are possible, and I recognize that material innovation will be crucial to achieve this. I believe that TomTest can be a small movement to generate momentum and inspiration for wider actions. Thank you.
Hi, I'm Dan.
I'm Bina. I'm Alex.
And I'm Emma, and we're the team behind Biodesign Challenge.
We want your help to publish our first ever book, Biodesign Challenge, a retrospective.
BDC is an international education program and competition that's shaping the first generation of biodesigners. We pair high school and university students with artists, designers, and scientists to envision, create, and critique transformational applications in biotechnology. Our projects have gone on to show in museums and galleries around the world, and many have served as inspiration for new companies.
The book will be a full-color celebration of work produced by the BDC community over the last 5 years. It will feature 28 projects that bridge art, design, and biotechnology. Not only will it include essays by our alumni, but perspectives from eminent practitioners in the field.
Newcomers will find a primer on biodesign and how it's shaping the future of sustainability. For those already familiar, the book will offer insights from thought leaders, including biologist Paul Fremont, curator William Myers, and many others. It'll also include a foreword by Paula Antonelli, Senior Curator of Architecture and Design at MoMA.
BDC has collaborated with organizations including Science Sandbox, the National Endowment for the Arts, the Parsons School of Design, and the Museum of Modern Art, where we hold our annual summit. We're publishing the book in partnership with the University Science Center in Philadelphia.
So, if you're interested in learning more about innovative and fascinating topics, or if you just want to be awesome and support the next generation of biodesigners, then this book is for you. Every pledge, no matter how big or small, helps bring us closer to our goal. Thank you for your support. We can't wait to share the retrospective with you.
Some of us human, some of us bacterial, some fungal, some archaean, some viral, some others. We come together, all now to become both one and many, to dissolve into our multitude. We exist simultaneously, entwined through one another, an infinite family of odd kin and kindred strangers, crystallizing through a myriad of bodies. This is a cellular ceremony from and to us all. We have been weaving our lives since the beginning. We have been knitting, knotting, sliding, fighting, living, dying, and remaking ourselves into this fleshy fat mat of molecular exchange. We are tiny ones, swimming amongst slippery membranes, in and on bigger bodies. We've become signaling networks, branching out, streaming up, dividing, multiplying, mingling skin and hair, guts and brains. Homo microbis, a chimera, with disproportionate limbs sprawling, siblings inside our organs, growing out of one another, cheering each other on, helping each other out, then eating ourselves.
Some of my favorite parts of your work are the sort of joy of creation, sort of reflecting on how fun it is to just create things that haven't been done before and the camaraderie that comes up. And also just sort of the sense of playfulness and joy that comes in even the darkest stories. I mean, in some ways, parts of Autonomous and Robot and Crow are both, pretty depressing, but I came away from reading both of them, both when they were first published and again this week preparing for this conversation, with just sort of a sense of optimism and the reminder that the future will have moments that are wonderful even when things are scary. So could you maybe talk a little bit about how you work that sense of sort of delight into sometimes slightly dark settings?
Well, I am easily delighted. And I do take a lot of hope from the real world. A lot of the work that I did in Autonomous and a lot of my other stories came out of following iGEM, which is another very similar to the Biodesign contest where students invent biotech, usually with an eye toward some kind of environmental remediation. And I also really believe that part of the role of science fiction is to get us thinking about, it's thought experiments, get us thinking about where we want what we're building in the labs to take us. And dystopian science fiction, we all know exactly why that's there. A lot of us have read 1984 or The Handmaid's Tale. These classic works of dystopia are signposts saying, don't go here. Just like see all of these trends that are happening right now. Like this is where they will lead. This is terrifying. Don't do that. We need to stop. But we also need the other side of that, right? We need stories about, okay, well, once we stopped The Handmaid's Tale, well, where do we go? And so I don't believe in utopia. Like I don't write anything where stuff is perfect. As I just mentioned, like, we get our perfect ecotopia future, but then there's slavery. So there's never a happy, perfect ending. But I do think that even writing a story where there are progressive changes in culture, even though there's, drawbacks, feels utopian at this point, especially right now. And so I really do make a conscious effort to focus on characters who are trying to fix things, people who become pirates when they realize that they can't work within the system, or people who become subversives because they realize that their environmental work is actually connected to a larger colonial project, which is part of what I'm working on right now in a novel. And I think, in a sense, I try to keep realism in there because instead of just taking you into a perfect utopia where we're all like blissed out and everything is perfect, because I do want it to be a roadmap. I want people to understand, like, even if you come up with a solution, you're just going to create more problems that you'll have to grapple with down the road. But I focus on characters fixing things. I focus on characters forming alliances and friendships, even if it's non-human characters, which happens quite often in my work these days. And I really want people to come away from my work feeling like there actually is something they can do, even in really dark times.
Hi everyone, welcome back to Biodesign Challenge Summit 2021. We are going to move on to our next group of students from the California College of Arts in the architecture department. So go right ahead with the video.
We faced many hardships in 2020 that called for us to rethink our relationship with the natural world. The COVID-19 virus exposed how microscopic threats can harm community across the entire globe. Here in California, we face massive forest fires that now occur almost annually. While we ponder these environmental disasters and their spread around the world, we still ignore about 70% of the entire Earth, the ocean. Many are unaware of another devastating pandemic that is taking place just below the surface of the coast. As we walk along the beach, remnants of life below the water literally wash up between our feet to reveal this major crisis.
Hi, we are the Urchigami team. My name is Lena Kudinar.
I'm Gitika Arora.
I'm Nidhi Patel. And we're from the Architecture Division at the California College of the Arts in San Francisco.
As individuals of a bay, we often see shells and seaweed that has washed up on shores we walk along. We wanted to take a moment to stop and consider the stories behind these items and how we could give back to our coast.
Kelp habitats are like the forests of the ocean. They're home to all kinds of marine organisms and are also a source of their sustenance.
Kelp can absorb 20 times more carbon dioxide than a tree on land and can grow at a rate of 18 inches per day, up to 115 feet, creating a towering habitat that serves various ocean fauna and even buffers coastal land from erosion. On the shore, we found the hard shells of sea urchins, sand dollars, and other mollusks, and flexible seaweed grown in sunlight. We thought about the properties of these materials and looked more closely at the ecology. Kelp forest, like any other living creature, depends on homeostatic balance to evolve. But within the past decade, a domino effect of multiple stressors has decimated 95% of kelp forests. In 2013, a mysterious viral disease called sea star wasting disease swept through the Northern American Pacific coast at an unprecedented rate, causing massive casualty to many star species. The loss of these keystone predators has allowed for exponential growth in the population of their prey, the purple sea urchin. Ironically, sea urchins are a delicacy, and one would think this is an opportunity human can exploit, but in reality, these urchins are not fatty enough to eat. They exist in a state of near starvation. These zombie urchins roam around the rocky ocean bottom, consuming the once lush kelp forest past the point of regrowth.
From an architectural perspective, we acknowledge our profession is also an industry of extraction. One of the most widely used materials is concrete, its active ingredient of cement, attributing to 9% of the world's carbon emissions, and at the end of its life, adds to the growing level of landfill waste. Efforts to limit the sea urchin population are currently underway, with humans acting as substitute predators, neutralizing them by hand. We met with Denise McDonald of Urchinomics, an urchin ranching company, and Sheila Seamus, Executive Director for Noyo Center of Marine Science in Fort Bragg. Urchinomics is employing out-of-work divers and fishermen to harvest live urchins so that they can be fed and raised, later to be sold to restaurants for consumption. Though these are valiant efforts to cultivate seafood, their shells and spines are discarded as waste. We wondered how we could use this waste as a resource and link a regenerative process to the commercially viable economy that can incentivize the removal of purple sea urchin, helping to restore kelp habitats and rebalance the ecology of the ocean. We also partnered with Renee Angwin, an urchin scientist at the San Diego State University Coastal Marine Institute, who sent us shells for experimentation. We became fascinated with both the physical and chemical structure of the sea urchin. The shells take on an oblate shape, composed of interlocking plates that provide exceptional compressive strength and the ability to withstand hundreds of pounds of pressure at the depths of the ocean floor. The microstructural layers of the urchin's thin shell are even reminiscent of brick and mortar. The shell is composed primarily of calcium carbonate and held together with a protein glue. At the end of an urchin's life, the acidity of the ocean waters break down the shells, releasing calcium molecules into the sea that can be reused in the formation of shells or coral of future generations. We can learn from a sea urchin's shell building process to rethink architectural form, construction methods, material composition, and a life cycle that culminates in a harmless or even benevolent manner. Urchigami envisions the merging of an urchin ranching facility and a farm-to-table dining establishment built out of the shells of the urchins themselves, creating a circular loop where the shells create the architecture. The site of Fort Bragg, California, ground zero for kelp deforestation, is home to a once robust fishing and former logging community. Our project seeks to remediate the issues of purple sea urchin overpopulation and kelp deforestation by developing a restorative building system in contrast to historic extractive human industries. This project provides multi-species benefits using the excess shell waste in the construction of two new building materials, gami sheets and urchicrete. Gami sheet is a thin, paper-like material composed of crushed sea urchin shells. Studies in parametric digital modeling led us to folding patterns that would give single sheets of flat, lightweight material a complex form and compressive strength. The efficiency of folding structures allows for a thin shell to act as both framework and enclosure, eliminating the need for external supportive material such as rebar or steel. We experimented at scale with stone paper, which is a readily available waterproof paper made out of calcium carbonate and a plastic binder. Substituting a bioplastic such as PHA for the current HDPE binder, this material can be optimized and scaled for building. This simple substitution would make the material completely degradable. We produce a variety of forms from arches to domes in our studies. The folded gami sheets act as a structural underlay for the spray-on urchicrete paste, applied in much the same way as a traditional swimming pool made out of concrete. With discarded sea urchin shells as the aggregate material mixed in with a live alginate binder, the paste can precipitate calcium carbonate. It is a restorative construction material used in a cradle-to-cradle life cycle.
Urchigami introduces a self-healing biocement building system developed in partnership with Dr. Achal from the Guangdong Technion Israel Institute of Technology, China. In the urchicrete mixture, live algae is combined with calcium carbonate sourced from local sea urchin shells. The use of live algae with high urease enzyme activity provides a conducive environment, with split substrates such as urea or amino acids added in the mixture for microbial growth to produce carbonate ions and ammonium. The increased calcium ion content of the urchin shells and algae will reach a level of calcium ion supersaturation, resulting in calcium carbonate precipitation or biocementation. Since gami sheet foamwork is composed of calcium carbonate, It will bind to its compatible counterpart urchicrete and seal joints and also strengthen the structural form. This biocementation process also features the ability for self-healing. Over time, as cracks appear in the hardened urchicrete structures, ammonium-rich water harvested from the urchin ranching process within the building can be sprayed over its exterior surface. This is yet another primary waste material that has the potential for reuse. Doing this will reanimate any surviving dormant microbes and reintroduce new aquatic microorganisms that can initiate the calcium carbonate precipitation and biocementation process all over again. Resistance to water infiltration can actually increase over time, and any cracks, pores, or openings in the assembly can be sealed with precipitated calcium carbonate. This also increases stability and reduces permeability of the enclosure. As generations pass and the issue of purple sea urchin overpopulation is mitigated, the structure can adapt to a new use and be repurposed or even dismantled and reused. Sited in a location rich with redwood forests that have undergone devastating fires, refined alkaline powder made from the dismantled origami buildings can be added to local soil. These soils have low acidity levels due to high amounts of wood ash, and the addition of the crust structure can improve the soil for better redwood tree regrowth. The cycle of origami is one that will be cradle to cradle rather than cradle to grave. In conclusion, the introduction of the origami building system to Fort Bragg provides a catalyst for a new economy based in the understanding of biological processes to help rebalance the ecology of the ocean. It is a design that is both rooted in our local environment yet relevant to other regions of the world. The vision of origami is to shift from extraction to regeneration. To do this, we must leverage our scientific understanding of how animals grow and self-heal, and find solutions that can help heal our impact on the world, from the redwood forests to the depth of the seas.
Hi everyone, Origami, if you can turn your videos on, great job. Do any judges have some questions? Fred, would you like to go first?
Okay, well, I really liked a lot of the things in this presentation. I guess I was a little confused about how everything fit together. You know, like how you went from the sea urchins to the design you came up with, how that reflected the sea urchin structure, but also there wasn't very much time spent on how you actually went from the sea urchin to that process with the algae to make the materials. So if you could comment on that.
Yeah, great question. Thank you. So the sea urchins, they're made of calcium carbonate. So that was kind of our starting point of what materials we had to use with. And the form of the building, it was kind of a separate interaction in which we looked at different parametric ways of creating architectural form. And what we found was this really beautiful origami shape that could create kind of a dome that was reminiscent of the urchin. So that was kind of the moment when we realized that this is a form that we wanted to go with, and this is the form that would represent both the material that we're using as well as kind of the plan that we have for the project.
And how is the material made?
So the material of the gami sheet is a calcium carbonate based paper, and it's 80% calcium carbonate, which we would source from the urchins, and 20% of PHA, which is a degradable type of plastic binder. And on top of the folded form, we would put the paste material or the mixture of urchicrete, and that's made out of calcium carbonate, the algae, and water as well.
Thank you.
Great. Do we have any other questions? Anya, can you go?
Hello, team. Great to see your work. I really enjoyed kind of the form, the final form, kind of circling back to the urchin form. kind of, to me, represented that circular kind of cradle to cradle concept you're talking about. I'm coming from a technical background, and I kind of had a question around your Urchicrete and how is that working? What are the roles of the urchint-based material, the calcium carbonate, and then the algae? Could you expand on that?
Sure. So Urchicrete is basically composed of three elements. So that is calcium carbonate, that which is 3 part, and then it's algae, which is 1 part, and water, which is about 1.5. So this, and we're using live algae in it instead of dead algae. So the live algae is used because of the microorganisms that it contains, which helps in the growing of this concrete, the Urchicrete, when you spray it on the cracks. So that helps it.
Okay, so to understand it sounds like the alginate or some sort of material in the algae will be the binder, similar to your paper, where there is some sort of polymeric binder.
Yes, that's right.
And have you looked at the mechanical properties of such a system? Like, just wondering about feasibility for like a building scale.
So algae, basically the algae that we are using at this point is the sea lettuce, which is invasive on the California's coast itself. So using that is going to, in California, they are trying to get rid of it. Not rid exactly, but it is edible and it is used for a lot of things, but it's still invasive. So that would be helpful. And also because concrete, we're trying to make this bio cement, and in general, cement has a lot of CO2 emission. So this process is going to stop it because there's no limestone in it.
So I can add a little bit about the structural properties. It would be something that's, since it's naturally made, it's more brittle than regular concrete, but since it does have a regenerative property, we can continue to build on that regenerative property.
Okay, I think we have time for one more quick question. Leslie, would you like to go?
Yeah, building on the last judge's question, have you tested this at all for not just architectural strength and durability, but how it would work as a structure where people work, live, eat, hang out, as far as heat and cold, all the architectural considerations. Have you worked towards that at all?
Well, I would say at a large scale of an architectural building, we haven't been able to test like the heat or thermal properties since we're doing small scale testing. But theoretically, since it's a coastal building and it does have apertures that are kind of open, it's more of like a shelter that's like a beach-side shelter. It's not something that's supposed to be perfectly thermally sound or not. It's not supposed to provide like a complete shelter for an individual. It would be more of like a open outdoor shelter.
Right, got it. Okay, thanks.
But still, on top of that, it's more like waterproof material. So definitely you get protection against rain. That's one of the solid parts.
Okay, good. Thank you.
Great. Well, thank you all for that presentation. Excited to see your project more at the gallery show later today. So next up, we have Zurich University of the Arts.
Soil is a peculiar thing. It is the dirt beneath our feet, the thing we all belong to, the thing wars are waged over, and the thing people are fleeing from. It is also a living thing that acts and practices politics with its ever-changing processes. Processes and entanglements we have much to learn from. I got the chance to collaborate with the Swiss Federal Institute for Forest, Snow and Landscape Research, WSL. I investigated what soil actually is and what its role is in our ecosystem. Swiss soil, for example, is over 15,000 years old. It developed when the glaciers retreated and left the rock exposed to the weather. Its nutrient cycles and the microbes that facilitate those enable plants and animals to thrive. It can take hundreds of years for soil to form. Once destroyed, soil is lost. Furthermore, soil is the largest terrestrial carbon deposit, meaning that if soil is disturbed, carbon is released into our atmosphere as CO2. This really shows the importance of soil in our climate. Later, I focused on soil respiration. I was fascinated that soil actually breathes. All the microbes, animals and roots in soil respire CO2, just like we humans do. It is therefore a basic method to determine how active the soil microbiome is. I experimented how to perceive this respiration with sensors and how to translate it into a material. I was interested in what soil respiration tells us about soil, its condition and its beings. I built a very simple soil kit, a respiration chamber that measures CO2 and has the potential to measure other gases, such as methane and nitrous oxide. Those two gases are even more important indicators, and making sensors for them readily available will be an essential step in soil research. Soil respiration devices today are extremely expensive and mainly used by scientists. My soil kit has the advantage of being affordable while also being open source. By distributing my construction plans and the code, my aim is to share knowledge to the broad public, democratizing scientific tools and bringing them into the hands of people. The price also makes it possible to deploy a soil kit in large numbers, which gives us a map of microbial activity. This helps us to understand microscopic metabolisms around us that drive larger ecosystem dynamics. Coming from a family that fled the war in Vietnam, I have always been investigating what it means to leave your land and your people, and what those landscape structures tell about the history that unfolded there. Therefore, I was sensitive to the social and cultural entanglements of soil. During my travels in 2020, I learned how the landscapes of Cambodia are linked in dense political webs. Deforestation, soil erosion, and other ecosystem disturbances are seen and felt everywhere. It was also the first time that I saw what it means when a forest burns, when you smell the gasoline in the air and feel the heat on your skin. I witnessed what it means when families are torn apart, when families are displaced, and when their livelihoods are taken away. I've never been to Hong Kong before, but when I first went there, it was oddly familiar to me. The food, the people, the language, all things that I knew since childhood. It's kind of surreal to experience that on the other side of the planet. In June 2020, I was invited by a friend to join the activities in Wong Chau, a village in the very north of Hong Kong. He was part of an activist and artist group that resisted the eviction of the village through creative practices. Together with villagers, they organized festivals, concerts, workshops, and more. And those activities were extremely important for everyone, as they created collective memories and shared knowledge. Especially now, since Wong Chau has been destroyed in the beginning of 2021. The richness of those practices demonstrated that they were not merely defensive acts, but inventive acts, involving new strategies and multi-species alliances on organization. The flow of life in small areas such as Wong Chau really teaches about the dynamics of this world. What we can learn from its struggles also conditions our collective survival on this planet. Through an attunement to our environment, we learn from its entanglements with history, culture, and politics. The landscapes, they tell stories of colonialism, of capitalism, displacement, and war. Noticing the stories and the common responsibilities we all share, I rethought and advanced my practice as a designer. A practice that is all too often focused only on humans, and a practice that we need to expand towards a more than human approach. Towards a design that benefits all beings, and ask how cultivation of shared responsibility dares to imagine otherwise.
Thank you so much for that great presentation. I'm going to turn it over to the judges if you have any questions. Fred, would you like to go first?
Okay. I thought that was very, very interesting. The apparatus that you designed sound like it could be incredibly useful, but you really spent very little time describing it. Could you describe a little bit more about how you went about making this object and why it would be democratizing?
I stumbled upon a few dual-use approaches for soil respiration, but I thought there and some papers that really describe it in scientific context, but there was never like a prototype that was ready to be used in the field. And so I was quite interested to designing this and to send this around, especially now that we couldn't travel this year and last year, to have a device that that is cheap, that you can democratize and send around to many people, that you can do measurements remotely. I thought it would be very valuable. And of course, like mentioned in the video, to have many of them is a tremendous advantage, or would be.
Mm-hmm. So you have tested it and shown that it's very sensitive and it's cheap to make and everything?
Yeah, we did a series of measurements, and also together with the Federal Institute for Forest Research and also with the Swiss Federal Institute for Material Research. We were evaluating low-cost CO2 sensors and how valid they are in soil respiration measurements. And they are quite accurate, because you don't measure like the precise amount of ppm. You measure the flux, so you measure the how the CO2 rises, and so it doesn't matter if it starts at 400 or it starts at 450 to measure. But within the increase, it is about plus minus 1 ppm, which is very, very accurate.
Thank you.
Great. Hi, Ryan. Did you want to ask a question?
Please. Thanks a lot for the presentation. I really appreciate the kind of very pragmatic sort of device that you've built on one hand, and the more kind of like philosophical approach that you sort of lay out in the second part. And I understand both are very much rooted in this concept of land. But can you maybe sort of draw out for us a little bit more the connection between the device and the kind of more social political elements that you're exploring in the video? And is there like an instance where sort of one informs the other, or how do you see that relationship?
So actually, my initial idea to make this device is because I was a participant in a village, like you saw in the video, and I wanted to continue my contribution there, but I thought I couldn't. So I thought of doing this device that could be sent there and then could inform how valuable that land is, that forest and farmland in Hong Kong, how valuable it is, and that urbanizing it, I mean, especially in Hong Kong, is really something you have to fight against. And that was my initial idea, also to democratize it
right? So you can have it at the hands of activists and artists and also citizens that could deploy it and then somehow show the activity of the land, and also maybe measure land in the village and maybe urbanize parks and show the difference there. Does it answer your question?
Yeah, I think so. So you're saying it can maybe reveal some element of value to that land that wasn't sort of recognized before. Is that what you're saying?
And maybe it's also to see the activity around us, the microbial activity in land, and I think, I mean, until now, CO2 measurements of soil respiration is just made like a few times by scientists, because they have to carry around very heavy and expensive devices. And if you can democratize those tools, I mean, there's a lot of room for imagination what citizens could do with tools like these. Maybe like applications beyond my.
Yeah, great. Thank you.
Thank you.
All right. One more question. Anya, you can go.
Hello, my name is Onye.
Thank you.
Thanks for the presentation. I kind of wanted to build up off of the first two questions and put on my bio arts hat and kind of ask you about an object. So you talk about this device that you made that can do measurements. There's colorimetric change. So I'm curious, like, what do you envision? How do you envision this coming together as a kind of something that the public would interact with? So to clarify, would you be simply kind of collecting some soil from local, like locales, and kind of demonstrating the CO2 flux or activity, or would you imagine this kind of being implemented into some like greater mosaic or some sort of object, that a designed object?
You mean, yeah. Well, I imagine it, like I said, to be a device you can build yourself and iterate on it yourself. And I think one of the things I envision is if you have many of those and you can place them and leave them in the field, it could give you like a micro map of microbial activity, you know, like a satellite map, but just now like a map of very tiny metabolisms, but that have great influence on terrestrial dynamics. I hope that answers your question. I'm not sure if I understood it correctly. Yeah,
there's no right or wrong answer on this one. I just wanted to know a little bit more about your vision.
Yeah, and I mean, you talked about the material, the color changing material. I think I'm at the moment doing more research into how you could use them in a meaningful interaction, because it indicates breath of bacteria, so to say, but also human breath. So if I breathe in it, it changes color as well. And I think this scale of indication is really awesome. I mean, to have a material that indicates metabolisms of such tiny beings, and the biggest mammals, very exciting. And I'm still figuring out how to bring this together in a, like I said, a meaningful interaction, not just a plaything.
Yeah, thank you for sharing.
Thank you.
Great. Thank you for sharing your project today. It was really great. We're now going to move on to the Universidad de los Andes team. So whenever you're ready.
Can you recall a family dinner where the topic de rigueur was climate change related to pollution, global warming, or water contamination? What if there was another wicked problem often unknown and overlooked? In 2015, the Food and Agriculture Organization of the United Nations reported soil contamination is one of the main threats affecting the world's land surfaces. The source of this type of pollution can be linked to chemical products used in agriculture, manufacturing, and even in military operations. These substances containing one of the primary sources of soil contamination, heavy metals such as chromium, lead, nickel, copper, cadmium, and arsenic, end up being released into the environment. But that's not all. Did you know that your garbage can contribute to this problem? After garbage is disposed, it usually reaches local landfills, producing leachate, liquids coming from waste decomposition containing heavy metal that seep into the soil and water. Despite the pandemic's limitations, we were determined to find a biosolution by co-working with a farming community. That is why we arrived at Mochuelo Alto, a rural community in the outskirts of Bogotá, Colombia's capital, located next to the city's landfill. Today, a population of 5,000 people depends on agriculture as their livelihood. They are directly affected by leachate metals, causing contamination in water sources and altering the soil's biodiversity. These metals also reduce organic matter, drive harmful effects in plants, inhibit growth, and nutrition assimilation in crops. The economic costs for the community are directly related to this waste problem by having low productivity and crop quality reduction. But did you know that even the most committed consumer faces risk due to the produce exposure and intake of contaminated vegetables and animal-sourced food? The impact on the consumer could be associated to health issues, as heavy metals are related to cancer and adverse effects on their nervous, respiratory, reproductive, and cardiovascular systems. Lixi Lab was born to empower small farmers who produce 70% of food in Colombia and who represent 90% of the world's agricultural community. We recognize the importance to bring the farm-to-table movement to this community and foster organic, seasonal, and local produce, supporting Colombia's farming communities. Lixi Lab is a grassroots, feasible bioinnovative solution, joining science, design, and systems thinking with empathetic design methodologies. Lixi Lab is a bioremediation technology using the bacteria Licinibacillus sphaericus CBN5 for extracting heavy metals in farmed soils. But how does this all happen? We co-designed with a Lixi Lab influencer. Licinibacillus sphaericus CBN5 is a bacillus-type non-pathogen bacterium. It is isolated from uranium mining waste piles and petroleum exploration sites, and studied for bioremediation purposes since its superpower lies in the fact that it is metal resistant. This sucker can accumulate heavy metals like lead, chromium, cadmium, arsenic, and even degrade hydrocarbons. What? Really? No way! An authentic bioinfluencer. But wait, that's not all. The bacterium works even if it's dead. Yes, you heard right, as dead bacteria. According to research, Licinibacillus sphaericus CBN5 absorbs metal after it has completed its life cycle, just like it did when it was alive and kicking, because of its self-assembling protein, known as the S layer, that can self-assemble in two-dimensional structures trapping metals in its microscopic holes. Additionally, it works with functional groups, which give bacteria its affinity to metal ions, facilitating metal adsorption. This layer is found negatively charged on the cell membrane. Therefore, bacteria can adsorb positively charged metals. Also, it has amazing advantages because of its lack of metabolic susceptibility by environment fluctuation given by undesired horizontal gene transfer from other microorganisms. The farmer community at Mochuelo was skeptical about introducing living bacteria into the soil because of all the bad rap it has, especially right now. Our technology applies the bacteria in a dehydrated hydrogel matrix made of a chitosan and alginate blend that works in water and soil. We chose those biopolymers because these are non-toxic, biocompatible, biodegradable, and are obtained in large quantities all over the world at a low cost. Lixi Soil, our first biotech application, contains a biofilter which prevents and diminishes the number of heavy metals in agricultural soils. It's designed to control contaminants on surface-rooted plants like vegetables and tubers, measuring up to 60 centimeters or 2 feet. After introducing it to the soil, a porous version of the hydrogel is inserted, and then water is added so that the bacteria can have better contact with the earth. This hands-on practical system works along with farmers' knowledgeable practices and tools. The root-inspired capsule design is buried in the soil. Its packaging contains chitosan and alginate spheres soaked with dead bacteria. The container is inserted into the ground according to the farmer's need. A fence with several filters can be placed individually at a variety of locations on the land. The design is easy to use. Just unwrap the package and insert the hydrogel spheres and water into the capsule. Leave leaky soil until the conductivity sensor indicates and refill with a new package or remove the capsule for seeding. After changing the matrix, farmers will return the packaging with the bacteria-filled metals for collection at indicated locations in public and communal spaces. Lixi Aqua is our second biotech application, designed for implementation in water sources used for irrigation, storage tanks, ponds, and other daily uses. It contains the hydrogel filter coated with dead bacteria. Lixi Aqua should be placed in the medium up to 1 day to do its filtering process. At the end of the sphere's life cycle, metals are extracted from the bacteria in a lab. The service is included with the product, in which trained professionals methodically remove the metals. The system is low-cost and uses a certified polymer biocomposite that is easily recyclable and has neutral carbon footprint. LixiLab's mission is to make toxic-free crops possible, increasing good health and well-being of farming communities and consumers, preventing heavy metals leaching from landfills, reducing the risk of people suffering diseases. LixiLab's Sustainable Development Goals shared commitments towards zero hunger by preventing waste and crop losses, and obtaining more fertile productive lands also guarantees the ecosystem's biodiversity and reduces land degradation. When comparing LixiLab to other soil remediation technologies as soil washing, thermal, and electrical treatment, it has shown that its biotechnology reduces human and environmental risks. It is low cost, and it does not require continuous maintenance, nor does it require fossil fuel energy or other finite resource other than the water or humidity found in the environment. LixiLab can also be useful in areas where mining has been conducted or militarized zones that have released heavy metals in the soil. Our professional team will keep working diligently to continue creating new biotech applications. Our next step is to reinforce the material matrix, creating a durable, tough product that meets quality standards and benefits underrepresented communities that otherwise would not have access to a bioremediation procedure. LixiLab, strengthening farming communities from the soil up.
Hi, Lixi Lab. Thanks for joining us today. I'm going to turn it over to the judges for any questions they have for you guys. Hello, Elena, would you like to go first?
Sure. Thank you so much for your presentation. This was really inspiring. And I'm just really curious and would love to learn more about your relationship with the farmers during your field research. And you also mentioned that there was some apprehension about using LixiLab in the soil and your product. And I just wanted to know how you were able to build trust with the farmers and how you're going to, in the future, share and scale your project.
Okay, thank you for your question. I'm going to answer it. And first of all, we've been working with this specific community for around 4 to 5 months. And we use empathic design tools to get closer to them, to understand how this problem is really affecting them. And because of that, we were able to build such a strong bond with them, such a really insightful experience for us, and powerful also because we're constantly prototyping with them, seeing how our design can adapt to their knowledge, their tools, their agricultural practices in general. And also we were able to, as I say, co-create a bottom-up solution with them. So it was really inspiring for us. It was a really nice experience in general. And after the contest, I'm sure that we're going to continue working with them to make this even more accessible and more a reality.
Well, great job building that relationship and having a working prototype. And yeah, congratulations.
Thank you.
All right, Leslie, I'll hand it to you.
I really enjoyed your presentation. My question is, what did you discover in your in situ testing? So when you used it in the real world, did you collect data and how did it work?
Yeah, well, thank you for your question. And first, we wanted to work with this community because we already knew that this problem was happening, but we wanted to understand better how it was really affecting them. That's when we find out about the problems that they were facing, like health problems or the crop losses. And we also did some interviews with them, with the farmers, and we tried to make a really complete prototype that could respond to their needs, and not only facing the problem that we mentioned earlier with the heavy metals, but something that they could really use and it could really work for them.
So when you did that, did you find it worked? And did it collect heavy metals, the device collect heavy metals and the bacteria from a certain distance? I mean, did you collect data when you actually tried the prototypes? Did you collect data on how well it worked?
Okay, so for that, our university has extensive research, that is lab research of this bacterium. It has been proven that it can absorb metals like we mentioned, chromium, arsenic, cadmium, up to 45% to 95%, depending on the metals. What we really prototyped with this community was the functionality of our design and things like that.
Okay, so not yet any follow-up testing on the actual function. Okay,
that would be our next step.
Sounds good. Thank you.
All right. I think we're going to move on. Lixie Lab team, thank you so much for presenting. Looking forward to seeing you all at the gallery show later today. Okay, we're going to move on to our next team, RISD, the Rhode Island School of Design.
In the world of ecology, we start with an ecosystem. Within an ecosystem, a unique type of interaction that can develop is facilitation, where the presence of one species alters the environment in a way that enhances the growth and survival of another. This isn't a simple give and take, it's systemic, beneficial change that relies on the creation of a framework rather than a simple exchange. And within the natural world, we as humans are not exempt or excluded from these ecological intricacies. What if we approached human institutions as an ecosystem in disrepair, out of touch with nature? Let us take you to an ecosystem dear to our hearts and in dire need of facilitation, our community in the northeast of the United States and our institution, the Rhode Island School of Design. The Rhode Island School of Design, or as we like to call it RISD, is an ecosystem of creative exploration and experimentation centered upon creators, the materials they use, and the spaces that house them. Students use all kinds of conventional and unconventional substances to create. But what happens after a project is over? What happens to those materials? What happens to the waste we generate during making? Where does it go? The reliance of many studios on toxic or synthetic materials makes reuse or recycling nearly impossible. Dyes, inks, and foams are produced, used, and then disposed of at an astonishing rate, especially at a school where experimentation and expansive prototyping is encouraged. When we looked at RISD's current waste management system, we noticed that food waste from the dining halls was going into industrial composting. While not the worst path for food waste, there is so much more potential in upcycling that could be done. The material waste from studio courses and department buildings is a different story, with the vast majority ending up in a landfill. So how can we link these two? How can we facilitate the reuse of food waste on campus before it ends up at a facility, and in doing so, offer a different material option to students, a more sustainable and biodegradable alternative? We propose a system in which selected food waste is segregated and converted into beneficial products such as dyes, packaging, and prototyping materials, which can then be used by various departments on campus. Let's take you through each step. The first node of the system is the dining halls and cafes on campus. They are a treasure trove of raw material. From talks with RISD dining managers, we found that the dining hall pays to dispose of more than 3,000 eggshells, gallons of coffee grounds, and buckets worth of vegetable scraps each week. These raw materials are then brought to the Nature Lab, the location of all material production. The Nature Lab at RISD currently houses material labs as well as biological references for students and has the facilities and expertise to help support the endeavor. Here at the Nature Lab, student workers will prepare the collected materials for further processing. With such a small campus, this program could easily be supported by students working in existing programs funded by RISD. We have identified eggshells, coffee grounds, seasonal vegetable waste, and specifically requested items to be the standard collection groups for RISD dining. These streams of food waste are all easily separated and can be diverted away from industrial composting. All of the collected waste types are processed and refined into their final materials. Eggshells are ground into a fine powder and then used in biocomposites, adding rigidity and structure to the material. Coffee grounds are boiled down in water to form this ink. The same process is followed for a variety of vegetable waste, being processed to produce concentrated inks. The residual coffee grounds and plant waste from the dye-making process are mixed with wood shavings from wood shops on campus and used as the substrate for mycelium cultivation. Mycelium is a mushroom network that is able to grow in a wide variety of material as long as it's given food. After inoculation with spores, the substrates are slowly enveloped with the mycelium matrix. At the end of the process, these microcomposites are sent to the different makerspaces on campus to be used as building or prototyping material upon request. Additionally, this growing mycelium colony can produce mushrooms for the dining halls, creating a circular loop. In modeling this new system of reuse around an ecosystem, a key pillar of this design is the circularity of many of the streams. Instead of going straight to the landfill, there are loops to recycle products, pulling more use and value out of our current waste. All leftover vegetable-based waste used in dye making is composted locally at a community garden, helping to support the produce grown and in turn re-enters the RISD dining system. With the basis for these materials being simple natural components, they can be easily reused or composted at the end of their lives. Instead of student projects being destined for the landfill at the end of the semester, reuse and material breakdown should be the goal. Each of the materials produced at the Nature Lab can then be distributed to academic departments and the RISD store for sale to students and the general public. The RISD store is the main source of art materials for students. This space is also open to the public and frequented by many professors and locals looking for supplies. With this as our outlet, we could help push these materials to a wider audience as well as help fund the system's operation. A big piece of this proposed system is the work that would be needed to maintain it. Over the last few months, our team has done the work to make the system run. However, in order to be a sustainable and long-term solution, the project needs constant student work. Including delivery and material production, the system would cost around $120 a week. This could be offset by the sales of material. Some materials could be sold directly to students and the surrounding community, while the school could replace many materials it already purchases and provide the material to students at no cost, further pushing the vision of more sustainable materials becoming the norm in the art and design worlds. This project also provides a platform to educate the RISD community about sustainable material use. Already, we've had multiple professors reach out to include the premise of this project within their curriculum. There's a desire for these materials and this way of working, both from students and instructors. In the past, when students have been interested in biomaterials or waste reuse, they have taken individual initiatives. With the new website, students can make specific requests to RISD Dining, facilitating sustainable projects that they're working on. The website also includes additional resources, including past projects and material recipes. This should streamline the process and lower the activation energy to get involved, allowing more students to share their knowledge and experiment freely. In the last few months, we have also had the pleasure of collaborating with a RISD professor to help instruct their class, giving the system a trial run.
So the workshop that happened was kind of a catalyst for students to start experiment with materials and thinking about materials as the medium of their design. So not only they were thinking about what to make, they were also thinking about the material itself. And I could see how the students got really experimental and into it. At one point, you look over the room and you see everyone like cooking something, and then students running outside, running to the mat, to the cafeteria to bring things and trying to incorporate that into their bioplastics.
One of my main ideas was to just be really experimental with like everything that I could do with bioplastics, and seeing what additives I could put in, how it makes the bioplastics feel, like how it makes them interact with other materials.
I guess it's also nice to just like know all the properties of what you're handling with. And I feel like it also introduces like new ways of fabrication. A lot of people were like, bioplastic, I didn't think that was possible, you know, having like a compostable material. Yeah, so by making this work, I think you're also spreading the word about the possibility of working with biomaterials.
Katya's class has produced some amazing work in only a few weeks. These projects, paired with other students working to integrate waste from RISD dining, are now in an exhibition on campus. Just this small case study demonstrates the potential, desire, and possibility of these materials' future implementation at RISD and hopefully other schools to come. At the heart of the Biocycles project is the act of facilitation and connection, of identifying the needs of the community and designing a framework to address current problems as well as laying down the foundation for a better, more sustainable future. While designed for the ecosystem of RISD, the system could be implemented within other institutions with a similar focus on making and artistic creation. With the Biocycles project, we aim to turn isolated action into interaction, separation into symbiosis, and individual intention into systemic, sustainable change.
Hi, that was great for the Biocycles team. Thanks so much for joining us. I'm going to pass it over to the judges if they have any questions. Fred, awesome.
Yeah, this was great presentation. I love the local part and the feasibility and all the interactions you had with stakeholders. Very nice. I just was curious about some of these products and how they would be made, like the eggshell. You didn't spend a lot of time on that, or how these coffee grounds would really become dyes that could be used by some of your stakeholders. Could you talk about that?
Yeah, sure. So for our eggshell bioplastics, we decided to provide students, we decided it would be more beneficial to provide students with just the ground eggshell powder and some of the binders that we would use, because we noticed that RISD students would like more flexibility with how they want to fabricate their materials and in what proportion they want to play with it. So we found that if we just take the eggshells and make it into this pre-processed powder and provide them with instruction on how to basically make something, but then also give them the freedom to experiment with that, that would be sort of what the output product of our end of the system would be, and the students would make their own material. So we would provide them with just the crushed eggshell powder and some of the binders. And as for the ink, the process for making the ink was just boiling down the coffee grounds, the spent coffee grounds, extracting a lot of the dye to make it concentrated, so just evaporation. And then we added, we experimented with a couple of binders to give it the sort of matte look. And then there was some more, I think, glue, or we tried to use different binders to get it to be more glossy. But yeah, that was the process, is basically just reduction and adding of some binders.
I think, additionally, I think that the idea of kind of not wanting to make something completely processed to give to students is trying to find like an in-between where you're providing them with enough activation energy, enough like pre-processing for them to do experimentation, because inherently these materials have their own properties that are not just like alternatives to foam, alternatives to wood. I think they're really interesting, and they propose like a new type of making, and sort of having this in between where you're making
like eggshell powder and then like a binder and providing it to students to make sculptures or make sheets and have that kind of freedom was something we were really thinking about.
Yeah, very nice. I like that.
Great. Onye, would you like to go?
Sure. Great to see what you all have been working on. I think just to touch on your last point, it was really responsive of you to, start thinking about your end user and kind of what they would want, and kind of providing them with raw materials. It's like a 2-for-1, makes it easier for you and makes it more interesting for them. Something that I was curious about, you mentioned replacement materials, foam, whatnot. What materials are you seeing, like what waste streams are you seeing that are leaving the university that you would like to replace with some of these products?
I think I know Annie will agree with me, blue foam is a huge thing that we would like to see leave RISD. And a lot of other like synthetic dyes and inks we found were a big part because RISD, like during our foundation year, we make a lot of drawings, a lot of ink drawings that are throwaway 30-second drawings that don't need to be high fidelity, like beautifully rendered drawings. And so finding that if we're going to throw all of these drawings away, finding material that makes a mark but doesn't necessarily have all of like the chemicals that a normal inks do. So those two, and Annie could name a lot, but yeah, we're starting with these, I guess.
Well, just on the foam concept, I know how much foam is used with like the CNC and everything. Have you all tested, like what material would you want to use to replace the foam? And have you tested it at all? Just kind of like put it in there and see how it works?
I think with the foam, we're looking, I think CNCs, there's a lot of material specifications about like machining that, but I think the mycelium shows some promise as far as, getting it to be machinable. Right now, the microcomposite, I think, could be more just like hand, like cut with a saw or sanded down, but not necessarily CNCable yet. Yeah. And to kind of expand on other avenues of like material use, a lot of stuff that's done in freshman year includes kind of like innovative ways of making. So thinking about like using the laser cutter or using like 3D printers and things like that. And what we did with the professor that we were working with actually was experimenting with innovative ways to use this biomaterial. So we provided students with a base recipe for a gelatin like biomaterial biocomposite. And then they started adding different kinds of like flowers or structural materials like fibers and things like that. And we were actually able to laser cut them. And we had like a very specific like specification. And because of COVID, we ended up laser cutting it for them. And then they ended up making like different kinds of wearables and things that probably in foundation year would have been made out of plastic or something that wouldn't be recyclable after and would just be thrown away. So it was a really, really interesting process. Yeah.
Great, thank you.
Awesome. Okay, thank you guys for presenting today. We are now going to be moving on to Nest Makerspace's team Agro Style. So whenever you're ready, Jeff.
Do you think about the hands that pick your produce?
The design of future sustainable agriculture must include field worker voices.
According to the CDC, about 100 agricultural workers suffer a lost work time injury every day in the United States.
But studies indicate that 78% of injuries and 74% of agricultural worker deaths are underreported to the government. Most of the data is missing.
AgroStyle, designing needed, innovative, and sustainable protective gear field workers deserve.
And this is the AgroStyle team.
Hello, we are a team of high school students from the Salinas area in Monterey County of California. We have been meeting remotely with the Nest Makerspace on Saturdays since January. We attend different schools.
Heat, pesticides, and climate change, growing dangers for field workers. Farm workers die of heat-related causes roughly 20 times in the rate of workers in all other civilian occupations. During the California fires last year, field workers continued to work in dust, toxic air, and exposure to COVID-19. Many did not receive adequate PPE.
In Monterey County, Latino children are 320% more likely than their white counterparts to attend a school near heavy pesticide use.
We wanted to hear different voices from our community, so we conducted a couple surveys. Our first survey was an Instagram emoji sticker story survey. 76 participants shared thoughts on what sustainable agriculture needs to focus on and whose voices should be heard.
These are the results of our Instagram survey. Top 2 areas of concern: ag worker protection and food waste. Voices need to be included in the conversation. Elderly and ag workers.
We created a survey in Spanish that was distributed to field workers at Good Farms in Watsonville. We received 8 surveys back from 20 that were handed out. This was during the peak of our first strawberry harvest, so we were lucky to have collaboration. What bothers you most while working? Most field workers said that wet clothes from sweat and damp fields was their biggest irritant.
What type of gear do you wish you had? The responses to gear needed focus on water-resistant clothing that was light and easy to move in.
We asked the field workers we surveyed to give their own ideas. This is an example of the feedback we received.
The agro-style approach. We created wearable solutions to fieldworker safety issues formed by feedback from fieldworkers themselves. We explored the sustainable biomaterial goals of kombucha leather and mycelium. The sensors we explored were microbit to track temperature and moisture, millifluidic sensors, and a 3D printed root study tool that can be adapted to be wearable biosensors.
Hydration solution, the hydro holder. Going into this challenge, I knew that my primary objective was to benefit agriculture workers in their practice on a daily basis. I know the field is very physically demanding from what my grandparents have told me in stories. As an athlete myself, I'm lucky to be aware of a number of resources that are used to nourish the body after intense activity. Using this knowledge, I decided to center my focus on making water more accessible and effective for field workers. Moving forward with these goals, I came up with my first idea. I first thought of what was currently on the market for athletes. The first thing that came to mind were the camelback water systems that are often used by hikers on their long treks in the mountains. I always admired those systems and used that as fuel for the development of my own invention. My second source of inspiration came from the runner's bands that both short and long distance runners use to hold the cell phone in place on their upper arm. I use one myself when I'm doing endurance training. Putting these 2 existing contraptions together, I made the first prototype of my wearable water system, the hydro holder. The device is meant to wrap around the thigh and support the weight of an average 16.9 ounce water bottle. In addition to being lightweight and sweat resistant, the apparatus is specifically designed to be on a part of the body that is out of the way for agriculture workers. In other words, it won't cause any extra fatigue or be a burden to wear whilst working in the fields. I'm currently in the process of building my second, more developed prototype, and there are several materials that I'm currently using. For the part of the holder that goes around the leg, I'm considering using kombucha leather, bacterial cellulose, and paper. As for the water holder itself, I'm in the process of designing an insulator made out of mycelium to potentially keep the water cold throughout the day. I'm excited to continue the process and development of my wearable water system. There's still a long way to go, but I sincerely believe that the end result of the hydro holder will be extremely beneficial to both the agricultural atmosphere and the environment.
When coming up with an idea to help the ag workers, I first looked into what the problem areas were. For example, the back, knee, and neck. I prioritized the knee problem, which is when I came up with BioKnee. The first thing I needed to do was to make sure the device was bio-friendly. After that point, I was able to look over the survey responses to find out what else the device needed. One of the most important things I discovered in most of the survey responses was comfort. With the help of Ms. Corinne, I was able to work with a few biomaterials that would be the most comfortable. Finally, we put it all together and the first prototype of the BioKnee is almost completed. Moving forward, I would like to grow with additional biomaterials for strength and flexibility. I'd also like to separate out components to add a joint hinge.
For my prototype, I addressed a few issues that were brought to my attention once I interviewed my grandma, who used to work in the fields. My grandma's name was Sylvia, and she was working in the fields ever since she immigrated to the US. The issue consisted of drastic changes in temperature that can cause heat strokes, for example, constricting belts and garments that become cumbersome, especially when having to bend down when picking produce, and the lack of awareness of dangerous levels of pesticide exposure. Sylvia mentioned how the weather would drastically change from cold to hot in a given day. With these specific conditions, I came up with a prototype that can mitigate these issues in the fields that have been overlooked for years. I worked on two pieces that work together: an integrative watch and a sensing jacket that measures temperature and pesticide exposure, which has an extra layer of length that extends in the back for additional coverage and protection. The orange stripes that outline my jacket are the cooling and heating system, which are activated by sensors that capture the body's change in temperature. The green flap is designed to address the tightening belt situation that Sylvia mentioned. I would imagine this material to be made from kombucha leather, a durable and sustainable biomaterial. The watch uses a microbit, which has a temperature sensing tool with an LED screen that can be programmed to activate a cooling mechanism when your body temperature reaches 99.9 degrees Fahrenheit. So I designed an adjustable and easily detachable watch with some key details that my abuelita Sylvia thought would be useful. The microbit itself can sense your body temperature and signify you need to stop working or drink some water. The LED screen can be programmed to show the command in Spanish, English, Mixteco, and Triqui. The wearable band can non-invasively detect the organophosphates, an indicator of pesticide residue, by turning a different color.
As a kid, I was raised in the agricultural world. My mom is a farmer herself, and because of this, I've been able to experience many different things, and I've also met many different people. Growing up in this world really lets you see the struggles of farm workers and what could be improved. Through these experiences, I've noticed that something that could be useful for farm workers is something to keep them cool and also provide better air quality. I came up with a face mask that not only helps them be cool, but also uses mycelium as an air filter. Since farm workers suffer more from work-related lung disease, I believe this air filter would help the pesticides stay out of their bodies and also any other form of small debris. To keep them cool, I decided to add a form of insulation in the forehead area, which will hopefully let them work more comfortably. By using mycelium and agar bioplastic, we were able to come up with this design. Agri-style gear would incorporate biosensors. We made algae string of sodium, alginate, and calcium chloride, which are conductive when hydrated. In the future, we will weave garments with algae circuits that turn on when wet to help workers stay dry and warm. We explored designing 3D printed root biome study devices. We hope that someday these devices might be used to grow genetically modified roots that sense and track environmental pollutants.
Think about the hands that pick your produce. Sustainable protective gear field workers deserve.
Agri-style aims to turn our attention to the needs of our essential field workers, as many face increasing dangers due to climate change and unjust labor practices. Without the data, there is no story. We need to collect information to prevent heat exposure, dehydration, and exposure to pesticides. Agri-style gear with embedded wearable sensors can help fill in the gaps. We appreciate the opportunity to share our journey. This is just a small portion of a bigger conversation to address the changes needed to better protect essential agricultural workers. Thank you.
Thank you.
Awesome job. That was really great to watch. Okay, I'm gonna open it to the judges once again for any questions. There's a lot to think about, I can see.
Well, that was a great presentation. I love the fact that you really went out and interacted with the farmers and you asked them what they wanted. And I think this wet clothes thing was a big deal. You came up with a lot of different things, but I just wanted to understand, you know, when you were coming up with the kombucha and other approaches to having this water repellent material for clothing, did you consider that that would actually be better than using something that wasn't biodesigned?
So I know in my findings from what I discovered when I was actually growing this material, I did come across a number of obstacles with using kombucha leather, especially for my design because I was planning to use that as a primary material. So some of the obstacles that I found were that it's not necessarily time efficient to grow because it does take 3 to 4 weeks for it to be fully developed. It's also moisture absorbent, so it absorbs a lot of moisture, and that's not necessarily a great quality to have given the atmosphere that we plan to put it in, because it does soften the material and make it less durable, and cold conditions can also make it brittle. So even if it's kept dry, the lifespan can only be about 6 months. So a solution that I came up with for my design specifically, which could also potentially be used for the other designs within our agri-style ideas, were to cover the leather with a thin paper surface to preserve it. Or another idea that we came up with was to create a chain-like structure with both the kombucha leather and with the paper that's a little thicker. That would make the system longer lasting and more durable. And it would also require less kombucha leather and therefore be easier and quicker to make. So to answer your question, I believe that this would be the best alternative to use, just because of the qualities that it has, with it being flexible to accommodate the physical demands of field workers. And it does resemble an average piece of leather when folded about 4 times onto itself. So yes, I do believe it is the best option.
What a great answer. Boy, you really thought about this. Thank you. That was great.
Okay, anyone else? All right, Onye.
Hello. Great to hear your work. I was really interested in, the number of different kind of design solutions that you're coming up with. I was curious, you worked with farm workers. How did they, what did they think about your design solutions? Did you get them to interact with these prototypes that you developed? So for example, the knee, bio knee, did you, did anyone kind of get to interact with it physically or kind of give feedback on it? Just curious, since you did get to kind of do that early surveying work, what they thought of the final product.
Unfortunately, we didn't get it field tested by the field workers themselves, but we did. We were able to create prototypes, and we used them ourselves. And we thought they were off the feedback from the field workers that we received from the surveys. We, for example, comfortability, to make sure that they're very comfortable. We used I'm trying to find the words here. Sorry, I'm kind of nervous. It's just actually, can you repeat your question? I'm sorry. I'm getting all.
Yeah, sure. No need to be nervous, and I think we're all just kind of feeling our way through this digital biodesign challenge. So yeah, I just wanted to know, you surveyed workers in the beginning to kind of, get their feedback. What are some important challenges that they're facing? What are some issues that they're having? And you came up with some solutions. So I was wondering, what did they think about the solutions that you came up with? Did they address their needs? Did they think it was feasible? Yeah, just wanted to, there's no, right or wrong answer, just kind of wanted to know a little bit more about that.
Yeah, so we weren't able to get back into contact with the field workers, with our finished product, or not finished product, but our prototypes. So unfortunately, I can't really answer the question, but I believe they would be pretty happy as we use their feedback from the surveys.
So my grandma, to answer your question, my grandma actually worked in the field, so I was able to contact her on my prototype specifically, and so that's where mainly I got my ideas to come up with my prototype, because she mentioned that she had some difficulties with her belt and the tightness with that. So I was able to come back to her and show her my prototype, and she said that she thought that it would be useful, and that once it's brought to scale, that she just that'd be great for use in the fields, because it had like some of the qualities that the farm workers thought would be useful. And
if I could just jump in here really quickly, both of my grandparents also worked in the field. So considering that my grandparents, besides COVID-19 restrictions, I was able to see them. And although I wasn't able to, because I didn't have my own prototype, I wasn't able to expose them to a prototype. I was able to expose them to the visuals of the prototypes and the materials to kind of give them a sense of what that would be like. And I introduced them to it and told them it was it was sustainable. And they both they both told me that it was great work and that they thought that this would really help other people work in the fields, considering their experience in the fields, working in their fields for their whole lives as immigrants coming to the United States. They said that it really addressed their own concerns and the concerns of most field workers overall, considering needs and face masks and stuff like that.
Yeah, not to take up too much time, but just to clarify, so was the part that they were excited about, was it the sustainability aspect of the products?
Yeah, it was definitely the sustainability aspect of the products, considering they're very aware, my grandparents, of the effect of the environment. They both go out on walks every day and pick up trash everywhere, and they see the effect it has on the community and the environment. So they were very excited, not only about the sustainability, but also about the function and benefit that it would have to most farm workers and their overall concerns.
Awesome. That was a really great discussion. So thank you, Nest Makerspace team. We are now, and judges, we are now going to be taking about a 15-minute break. We will be showing videos during the break of past BDC projects, videos from artists and designers in our community, and information about our sponsors and more. So stay tuned, and we'll see you in about 15 minutes.
We like to define things by what belongs and what doesn't, because change means uncertainty, and uncertainty can be daunting. But stopping change is as impossible as stopping time, and focusing on the impossible is a distraction. What if instead of exclusion, we strove for balance? What if instead of eradication, we focused on utility? What if we embraced our environment the way it is, and we kept embracing it as it continued to change? And what if, when we stepped in to help, we did it not to destroy what doesn't belong, but to put what's out of balance to good use? We need to make invasive species material sourcing as commonplace as organic, post-consumer recycled, grass-fed, free-range, biodegradable, free trade, VOC, and hormone-free. It needs to be policy. But first, it needs to be designed. In our region, the Great Lakes region, the introduction and proliferation of zebra and quagga mussels have overwhelmed native species, their habitat, and our infrastructure. Efforts to remove them have been ineffective, and in some instances, even more harmful to the environment. As color and material designers, we wondered, what might happen if we treat them not as a biological threat, but as an overabundant material? We asked, what are they made of, and what can we make from them? Mussel shells are 95% calcium carbonate. Take them up to 1,000 degrees Celsius, and you get calcium oxide. Calcium oxide, lime, sodium oxide, soda, and silicon dioxide, silica, make glass. As bioaccumulators, zebra mussels filter the water. They filter out pollutants and plankton, minerals and trace metals, some of which give glass its color. A glass derived from zebra and quagga mussels will express the color of their ecosystem. Invasion, to region, to chemistry, to color, to identity, to belonging. We collected the first batch of mussels from Lake St. Clair, where zebra and quagga mussels were first introduced in the 1980s. Hitching a ride on ballast tanks of cargo ships from Russia and Ukraine, we boiled them, cleaned them, ground them up, and sifted them into a coarse powder. We worked out the chemistry, the molar calculations for mass and batch recipes. We designed the kiln program to pause on the way up to control the release of CO2 and H2O as sodium bicarbonate transforms into sodium carbonate, which transforms into soda, and as calcium carbonate transforms into lime. And as we paused on the way down and modulated the rate of cooling to swiftly transition through the vitrification range and to slowly drift through the anneal. It turns out the color of Lake Michigan glass is the color of icebergs and tropical atolls, the color of water. We're told it's a copper blue from the high copper content of Lake Michigan. It's beautiful, and we can't wait to see the color of Lake Superior or Lake Ontario. We can't wait to see each lake, comparing glass from the beach to the lake bottom, taking a biochromatic tour of the water column. We can't wait to rediscover our region through the brilliant blues or greens, or even yellows or rose pinks of what we keep calling an invasive species. And we can't wait to see what we can make out of zebra glass.
Hi, I'm Dan.
I'm Vina. I'm Alex.
And I'm Emma, and we're the team behind Biodesign Challenge.
We want your help to publish our first ever book, Biodesign Challenge, a retrospective.
BDC is an international education program and competition that's shaping the first generation of biodesigners. We pair high school and university students with artists, designers, and scientists to envision, create, and critique transformational applications in biotechnology. Our projects have gone on to show in museums and galleries around the world, and many have served as inspiration for new companies.
The book will be a full-color celebration of work produced by the BDC community over the last 5 years. It will feature 28 projects that bridge art, design, and biotechnology. Not only will it include essays by our alumni, but perspectives from eminent practitioners in the field.
Newcomers will find a primer on biodesign and how it's shaping the future of sustainability. For those already familiar, the book will offer insights from thought leaders, including biologist Paul Fremont, curator William Myers, and many others. It'll also include a foreword by Paula Antonelli, Senior Curator of Architecture and Design at MoMA.
BDC has collaborated with organizations including Science Sandbox, the National Endowment for the Arts, the Parsons School of Design, and the Museum of Modern Art, where we hold our annual summit. We're publishing the book in partnership with the University Science Center in Philadelphia.
So, if you're interested in learning more about innovative and fascinating topics, or if you just want to be awesome and support the next generation of biodesigners, then this book is for you. Every pledge, no matter how big or small, helps bring us closer to our goal. Thank you for your support. We can't wait to share the retrospective with you. Hi everyone, welcome back to Biodesign Challenge Summit 2021. I'm excited to introduce the next team that we are going to be viewing this afternoon. They are from Design Academy Eindhoven. So here we go, here's their video.
Playing with dirt, contrary to contemporary belief, is good for you. Early contact for children with soil has been proven to boost immune responses and increase serotonin levels. But even people who spend time in nature are getting exposed to fewer and fewer types of microbiota. As designers who have been based in the Netherlands, we look to this soil context, and Rotterdam in particular. Rotterdam is a space where numerous industries have taken place. Much of the soil in this part of the country has been polluted. Biodiversity across all aspects of life is decreasing, an example being 70% decrease in insects globally. There is a need for rediversifying our urban spaces to act as carbon sinks and biodiversity hotspots. But wouldn't this require immense logistics and communal trust? We propose the Dirty Playground. The Dirty Playground positions play as a multi-species activity that unravels over time, positioning probiotic design for public space. It suggests using ecological succession as a framework for multi-generational use. Through the process of ecological succession, the playground soil microbiome over time resembles the richness and biodiversity of a mature forest. In Rotterdam, for a playground to be made, it has to be voted on by the community. For the Dirty Playground to happen, we first identified community centers in the local area where we could collectively choose the site. We collaborated with a soil microbiologist from the Wageningen University to gain a clear picture of what the soil topography is like in this area. A section of public space is selected and chosen for the task. The first stage is an analysis of the soil. If the soil is contaminated, bioremediation takes place in the form of a watery swamp park. Oxygenated water is channeled into the groundwater below the soil, using play tools designed to allow people to take part. Once remediated, it's time to begin the laying of the forest floor. To nudge the process of ecological succession to reach a beneficial state, healthy soil is brought from a neighboring forest. By inoculating ecologically poor soil with mature soil, this enables the surrounding area to reach a mature stage of biodiversity faster. A messy meadow then grows from the inoculated soil, full of perennial flowers. At this point, we begin building the playground. Using some of the remediated soil, rammed earth structures are built with the local community that selected the site. These structures are built with biodiverse, rich soil and provide practical tools for play. By applying rammed earth techniques, play becomes an intergenerational creative activity. Plants and trees are then planted from the local territory, leading to the stages of a young forest. Over time, the young forest is replaced by a mature forest, and the soil microbiome has become enriched and similar to the donor forest it received its ecology from. Every year, if rammed earth structures need to repair, they can be mended by the healthy soil around, recycling the soil and ensuring children have a wider access to a growing, healthy forest microbiome. The Dirty Playground signals a shift in which longer natural processes, such as succession, need to be addressed as a crucial element of urban design. On the city scale, it shows how our timeframes for built projects need to adapt to allow for more than human kin to thrive in our urban spaces. By designing a public recreational space with stages of succession, we see the potential of urban space becoming inclusive to all forms of life, strengthening and sharing our soil heritages, and a new approach to rewild cities.
All right, that was a very interesting project. Thank you for showing that. We are now going to go over to some judge questions. Harris, I see your hands raised. Do you want to put your, yep, there you go.
Great, yeah, I thought that was really fantastic. As someone who's works on the microbiome and have small children, some of the messages really resonate with me. I was wondering if you could speak a little bit about some of the possibilities for feedback loops, you know, in terms of maybe opportunities to actually study or test the actual microbiome in terms of the diversity that is introduced, or maybe how you could potentially get some information also from the kids that are actually playing in the playground in terms of whether they're actually picking up some of these that might have some benefit.
Shall I go, guys? Yeah.
Sure.
So one of the research papers that was really influential in the for us, at least in the development of this project, was actually a Finnish study that essentially had changed the ground of a playground with like just some grass and a little bit of soil from a local forest. And the researchers analyzed the children's microbiomes on the skin mainly to see if there was a significant difference, and there was. And so what we were really interested in kind of working with was this principle, at the same time also with the idea that there's different types of microbes, specifically bacteria in soil, that kind of stimulate kind of happiness, let's say, just to kind of really gloss over the science part. But basically, this is what we were kind of working with. And with the idea that getting to a forest takes a lot of time, of course. But what's interesting is throughout the whole process, whether you're in kind of a swamp-like beginnings or going to a young forest and then to an older forest, that the microbial community changes through that time. And so, yeah, I don't know if that answers your question, but maybe
something to add on, because you were talking about the feedback from children and from the community. One essential part of the whole project or concept is that we would involve the community in the building of the different parts of the playground. So they would accompany the whole process of building it, and then also all the different stages of succession would be constantly accompanied by the community around. So the feedback is constantly there, and it's not that we as designers come there and put something there and then leave it to the rest of the world to deal with that. But the idea was really to work together with the community on all stages.
Mm-hmm. Acting as facilitators within that process. So it's as much a feedback loop between us and the community, as well as the microbial communities and the people that interact in the space. Lots of feedback.
Great, thank you so much.
Jason, I see your hand is raised.
Hi there. Again, yeah, thank you for the beautiful presentation. I thought the drawings were gorgeous and very thoughtful. I sort of had a similar question. I kind of wondered how many like parents you talk to in your different areas of the world, because I know you kind of live all over the world. Because there's just so much in design right now about voice being important and not making any assumptions about what people actually want. And so I know you were talking about doing that as you get started, maybe in a site, but I wonder just how much kind of as part of your research you spoke to parents from people of all different backgrounds and cultures, because I know you come from 3 different places. So that's my question.
I would maybe, as a step parent myself, actually, I have local to Montreal, like knowledge to the local community here, but I think we decided to really want to work with the Rotterdam community because of the specifics of how it's usually any playground that comes about in the city stems from community involvement and the community wanting to come together and implement this. So in terms of our knowledge and understanding of that is based off of us living in the Netherlands, specifically. So we were in Eindhoven, so we understand, of course, the Eindhoven, or at least the Dutch context, and Coltrane specifically moved to Rotterdam and lived within that area for a little while. So it is based off of experience, but not, I would say, direct, intense community involvement, because I think the first thing we were trying to wrestle with was actually where in our different cities would this make the most sense. And so I think from the way in which the like political structure in which like the playgrounds come about in Rotterdam, we thought we would start there.
I think to add to that, there's a sort of a fear of the soil within a sort of Dutch context. It's kind of told to you, don't play with the soil because it's contaminated, it's bad for you. And that's sort of ingrained into just people's sort of psyche or consciousness as it's passed down. Of course, a lot of sections of urban space are now decontaminated, but say 50 years ago, that wasn't the case. And that was an interesting point because we were trying to put forward sort of probiotic design as a useful tool within for urban space. And how do you design for urban space where the collective consciousness is around biological life being dangerous for you? And the location that we selected was in Oud-Westen, or New Western Oud-Westen. And it had, I think what was interesting about the Rotterdam in particular is it's the most child-unfriendly city in the Netherlands after the Second World War. So because it's made space for a lot of cars and there's a lot of lack of access to green space. But in a study done on playgrounds within the Netherlands and particularly Rotterdam, it was shown that people were less willing to actually engage in green space and were more active in sort of concrete areas. So within those sort of urban contexts, how do you sort of generate or create a sort of slow succession of warming up to the idea of probiotic public space as a benefit for everyone? That's kind of where we're going.
Thank you for that.
Welcome.
Great. Ryan, I do assume you have a question. We're a little over, but feel free to ask a quick question for the team.
I appreciate your consideration of the sort of cultural context, particularly of Rotterdam, which is a really dynamic city. One other context that I think is important to consider that I'd like to hear you talk about is the fact that it's famously rainy there as well. So how does the dirt playground not just become a mud playground? And what's the, how are these things actually built? I guess I don't think you really heard much about that.
So it's famously rainy, but the way that they've kind of, it's not muddy. How can I say? For having lived there for at least 2 years, yeah, it doesn't actually get that muddy, to be honest. But the way that the things are designed was actually the first thing we thought was, okay, rammed earth in Rotterdam, like super wet. Why does this make any sense? And so we started also looking at what are the kind of advancements that have been made in terms of rammed earth as a contemporary building material. And when it comes to architecture, it's a little bit more complex because of obvious reasons of having to control temperature, control humidity levels inside of buildings. But when it comes to playgrounds, you don't really have to worry so much about those things. So the way that you can work with rammed earth now makes it possible to, in a more wet context, to do these kinds of things. And there have now been more and more research and projects made with rammed earth in the Netherlands. So the way that we kind of imagine this is structures that are play structures. So in terms of scale, does not exceed what you normally see in a playground, in a, let's say, Western playground.
Okay, thank you.
Awesome. Well, that was a really fascinating project, you guys. Thank you for sharing. We are now going to move on to the next team from University of Illinois at Urbana, Champaign. So whenever you're ready, Jeff, we can.
Every year, 300 million tons of plastic waste are produced, and as a result, there is expected to be more plastic than fish in the ocean by 2050. And that's not the only pressing issue local waterways face. Large algal blooms threaten the very nature of our ecosystem in a process called eutrophication. As the algae dies off, bacteria feed on the remains and deplete so much oxygen from the water that fish and other aquatic life suffocate. In Illinois, these blooms are formed due to chemical runoff from sewage treatment plants and corn and soybean farms. Around 60% of lakes in the state suffered from phosphorus or algae pollution in 2014. Even in our local Champaign-Urbana community, recent reports from locals describe unpleasant scenes of dead fish floating atop water packed with blue-green algae. Fertilizer runoffs are destroying waterways, not just in Champaign, but all around the country. From a 7,000 square mile dead zone at the mouth of the Mississippi River to Toledo, Ohio, where the water supply of 500,000 people was forced to shut down for 3 days due to dangerous levels of contamination. And this is just the beginning. Algal blooms are projected to become more frequent in the future due to pressing issues of climate change, such as warming temperatures and rising carbon dioxide levels. Our team dared to ask, what if we looked at the algae problem as an abundant resource? What if we could use biodesign to tackle both problems, plastic accumulation and eutrophication, in one material solution? Crealgae aims to mitigate Champaign's contribution to this large buildup of algae by creating a fully biodegradable, algae-based bioplastic. We fall under an umbrella organization, Illinois UniAndes. Illinois UniAndes is an organization that aims to use the power of entrepreneurial action to transform lives and shape a better, more sustainable world. The idea for this project was developed during the UniAndes capstone experience.
Our diverse team of 13 members are from all across campus, spanning 4 colleges and 10 majors. We have 2 project managers, an executive manager, an operations liaison, media liaison, design advisor, 5 project associates, and our 3 project fellows. Our project associates drive our work through a variety of deliverables, from assessing market research to exploring potential revenue streams to branding. They also prototype on a weekly basis, along with our project fellows, who have further expertise in material science. During prototyping sessions, our team is always working to identify strategies to improve our recipe. The Fab Lab is our home for prototyping. Here we have access to a variety of tools, from 3D printers and laser cutters to embroidery tools. In the back, we have our biomaking space. This is home to our Enactus Biodesign project. We collect our algae from Boneyard Creek, a local waterway on campus. Sifting through our water samples and debris, we isolate the algae for our plastic. The samples then go to the Fab Lab, where they are dried in the dehydrator. Algae is then made into a fine powder using a blender. Algae is one of the most efficient organisms known to sequester carbon through its natural growth. Our process is water solvent based, so our algae, plasticizers, and additives enter our water bath. The mixture is then heated with a hot plate, allowing molecular bonds in the algae to denature, and the plasticizers to cause repolymerization at a productive scale. The molten mixture then gets poured into molds and dehydrated to achieve the desired product. Our team has ideated many practical uses for Crealgae plastics. We've identified a number of plastic consumer products that would be popular on our college campus, such as frisbees, cups, and reusable containers. Crealgae plastic is unique because it can be manufactured to have a wide variety of shapes, sizes, and structural properties. This means Crealgae plastic can be used for nearly any function and can replace significant plastic waste. Additionally, Crealgae is in talks with several local businesses that produce products with plastic internal components. We plan to have a business-to-business plastic properties catalog containing different options for strength, rigidity, and flexibility that companies can choose from for their custom components. No matter the application, Crealgae has a biodegradable plastic to fit the job. There are currently biodegradable plastics with similar material properties available in the market, some even made from lab-grown algae. However, Crealgae is the only one that collects the algae from the source to eliminate waterway pollution in a twofold approach. At this stage, our target customers are individuals and small businesses that are environmentally conscious and willing to pay slightly more for products that are better for the environment. And from our market research results, this demographic is present in our local community. With over 300 project hours just this semester, 13,500 grams of algae collected, and 350 grams of bioplastic made, Crealgae is progressing rapidly. We are always looking for new thoughts and people to be involved with our project and would love advice and expertise from anyone in the BDC community.
awesome. Wonderful job with that project. I liked the background music. It was kind of jamming. Does anyone have any questions for Creology? Leslie, how about you go first?
Hey, hi, thank you. That's a great project. I have a question though about when you harvest the algae, it doesn't necessarily take care of the phosphorus problem. What happens then in the waterway with all the phosphorus still coming in from fertilizer? And have you looked into that? What happens? I mean, obviously you're removing the algae, but then what?
Yeah, so we are currently looking into that problem. We obviously can't tackle all aspects of the issue, but hopefully by at least harvesting the algae, we can remove the harmful effects that the algae directly causes to the environment. We do recognize, though, that we aren't totally mitigating the phosphorus issue.
Thank you.
Onye, would you like to go next?
Sure. A follow-up to the previous question. I'm curious if you can share, I guess, how much, or if you've looked into this, how much algae would you need to pull out of a waterway in order to have like a measurable impact? Just thinking about, the rate of reproduction of algae and, kind of like, would you be making a difference? And also, second question would be, what would be like the percent algae composition in like the dry, like the solid material that you're filtering? I noticed that you maybe collected about 3.5 kilograms, but you only got around 300 grams of bioplastic out. So I don't know if that, is the conversion efficiency, but yeah, just wanted to know a little bit more about that.
Yeah, so as far as the specific details about the impact, that's something we're currently looking into. We're trying to use life cycle analysis software to try to figure out how much of an impact we're actually making, just so we can assess if it's actually even worth it to be removing the algae from the environment. And as far as how much of that algae is being directly turned into bioplastic, we collected a large amount of algae at the beginning of the semester, but didn't end up using all of it to create our samples because we all had to return back home after the semester was over. So the remnants of that algae will be used next semester to create more samples. And as far as in one specific sample, how much is algae? It is around 80% algae and then 20% plasticizers and other material.
Thank you for sharing that. Could you also maybe speak to the appearance? I noticed that there's like this blackish kind of like coarse appearance. Where does that come from? Is that from your plasticizer, or just kind of aggregate material that's co-filtered?
Yeah, so right now it looks like it's kind of like a black or dark green based on the algae. That's seemingly what's causing it, because our plasticizers are white and powdery, so they don't really impact the color all that much. We are kind of experimenting with maybe adding different like dyes, possibly looking into more eco-friendly dyes that don't really negatively impact the environment right now.
Great. Thank you.
Great. Thank you, Nikki. All right, I think we're going to move on now to the next project from Universidad Autonoma Metropolitana. So their video is up next.
Our great master of transmutation, Gaia. How to learn from her, how to transmute with love all we have caused. The breaking of the waves remind us of the damage we have done. However, we remain indifferent to the pain of our cause, which run to the beautiful community of Playa del Carmen, one of the most affected places by the annual arrival of Sargasso, causing the distinctive turquoise color of its seas and its paradisiacal views to get lost inside of it. Playa del Carmen, a city in Quintana Roo state in Mexico, belonging to the Ribera Maya, has as its main economic activity the tourism, thousands of tourists annually arrive from all over the world. However, due to the lack of awareness about the care of ecosystem, various problems of environmental contamination have arisen. The most serious being the arrival of tons of sargassum to the beach, an invasive macroalgae that causes many problems to the wildlife and the tourist industry. The large quantities of sargassum that annually arrive have been increasing. It's so many that collectors picked 2.3 tons just in the first 6 months of 2021. The characteristics of these algae have caused the disgust of tourists who look for activities that involve contact with nature, thing that is difficult to do with excessive presence of sargassum, ending in thousands of posts on social media about this, causing an unfavorable reputation of Playa del Carmen and thus a decrease on economical activities. This situation affects the community on a huge level. 7 out of 10 people say being affected economically, half of them saying on a big scale, even though their jobs isn't related with tourism. The ones that are affected the most are hotel workers, hoteliers, and restaurant owners, who had between 30 and 40% loss on their profits. This is why these sectors makes daily pickup of sargassum as a temporary solution. They are now even held by the Navy with 4 cargo ships, which can help in its totality. Knowing this systematic problem in Playa del Carmen, we came up with this question. How may we make a better use of sargassum to promote a sustainable development of Playa del Carmen community? With this in mind, the 3 of us, designers, start working about our design process and experimentation with sargassum to link both design and biology. From this, we created Espacio SAC. Our name is to honor the Mayan culture, which is located in this area. SAC means either venom or medicine, to poison or cure. It depends mainly on the meaning the user wants to give. This is what we plan on doing, to make the sargassum the cure and medicine of the community, instead of the current poison. Espacio SAC is a recreational space located in the beach of Playa del Carmen, especially to carry out activities around sargassum, such as biomaterial workshops, recreational ritual, etc., all with the intention of transforming the perspective that is around it, as well as serving as a new tourist space that will promote sustainable tourism and create a new kind of interaction between sargassum and tourists, and thus awareness about the problem. This is planned as an sculptural space made with our biomaterials, inspired by the ocean waves and the light interaction of water, accompanied with illuminated sculptures of marine species, to create an ethereal underwater experience. Our sargassum-based biomaterial will be our main material, using our structure and the activities around it. This material is sustainable thanks to its natural ingredients. Also, the end result makes an optical illusion of being underwater with sargassum. Multiple activities tourists can enjoy. Charts of people from the community are planned to take action inside Espacio SAC. Some of the proposed activities are: offer the space as a yoga and meditation area in the morning. This to reflect the impact of our action in nature and connect directly with it. The next activity is planned for children, which we find very important to include because they can learn from an early age that sargassum can be a friendly material. We will provide with a cartoonish character made with our agar biomaterial for the kid to customize with accessories and complete creativity liberty. At night, the space will serve as a show stage for sargassum ritual. It's planned to be accompanied by dance and light shows, taking advantage of our space characteristic of translucence and acting as the main stage, all around sargassum recollection. Espacio SAC will have an inside store, where we will offer locally made products and art. We will also sell the Espacio SAC book, which will be made from sargassum pages, and it will contain removable sheets of biomaterial, to invite our user to continue with the experimentation and its relation with the problem from home. The sale of our jellyfish lamp, also using Espacio SAC, will be able as a souvenir of the experience. They will be produced and sold by local artisans as a way of promoting Espacio SAC, and to generate an economical support to the community. With Espacio SAC, it's planned to intervene in the routine of the tourists, from the first moment where they start booking the trip until the moment where they arrive and feel attracted to visit the space. They part in the workshops, consume the offered products, and share their experience on social media. Espacio SAC is planned to bring benefits to the community, being the most important the increase of tourism thanks to the positive diffusion. Also, new opportunities, local product consumption, and cleaning of natural areas. As mentioned before, one of the greatest benefits will be the generated jobs. For example, hiring of sargassum specialists and biologists that will help directly with investigation and experimentation. The personnel in charge of the activities that will be developed in our space, guides and hoteliers will also help with the promotion of the space. Now, where to start? First, we need to contact the community further to provide tools and information about how to make and work the biomaterial in order to create new activities and appropriate the space as part of the community and continue with the project. In the future, we plan the space to grow and become a space dedicated to research and transformation of sargassum, but also an important touristic location that will help the community and change the perspective around the sargassum. In the same way, the project could be replicated in different beaches not only in Mexico, but all around the world. We know that Espacio SAC will not resolve the problem in its totality, and that this problem will keep existing and even increasing. But for us, it is important to reinforce the message and intentions toward the space, which is to generate consciousness about the consequence of our own actions. We think we can all place a drop of water to slowly become a sea, or even an ocean of change. We can all help Gaia. We can join the change.
Hi everyone, that was a great presentation. I am going to once again turn it over to the judges for questions. Elena, go ahead.
Hi. Thank you for your presentation. Super interesting project. I guess my main question is, have you been in dialogue with the local community about your architectural structure, sculpture on the beach, and how they feel about that, using the waterfront in that way? And have you thought about having your structure in any other locations?
Yeah. Hi everyone. Sorry. Well, thanks for the question. About the first question of the community, yes, we have been in touch with them since the beginning of the project. Actually, Majo's family lives there, so from there we have this direct approach, and we have also been in contact with hoteliers from there, and they are very excited about the project. Of course, the problem of sargassum is a very important issue for them, so they are really excited of our project and this solution that we are trying to give, of course. And about the replication, well, first, the problem of sargassum here in Mexico affects other beaches. We chose Playa del Carmen because of the contact, but it affects all the Riviera Maya. And even in the Caribbean coast, it affects other countries like Argentina, Brazil, and even in Japan, you can see this problem. So the replication in that way, it could be really easy. And even in the beaches that this problem of sargassum doesn't exist, it could be replicated because at the end, the message we are trying to give is the environmental care and the repercussions we are causing. So, well, this message is something that we want to spread all over the world. so we can take the structure in other places, of course.
Great. Fred, go ahead.
Yeah, I thought this was a great project. I mean, turning something sort of a pollutant into your beautiful ideas about structures. So culturally, very, very interesting. I agree that the community has to, of course, be on board. Just a technical question. You showed sort of one picture of the actual material that could be made. And I was just wondering how much you really know about the integrity of that material and how long it could last and such.
Well, you go. All right. The experimentation was quite exhaustive, if I can say it like that. So yeah, Maho was the one with this material, and we noticed that the material can be very sturdy and very durable, mainly if the thickness is varied. So long term, it hasn't had like any sort of issue, mainly because we've been like 3 months on it. So yeah, pretty much it's very durable, very strong, and it's okay so far.
Thank you.
The properties are to hardness, and the hardness depends of the material thickness. And other things we observe in this experimentation is that it reduces the thickness of more than half its size, and the smell disappears. What is very important because the sargassum have a very bad smell.
Okay, thank you.
All right, we have time for one last question, if anyone has one. Harris, go ahead.
Yeah, I had just a follow-up question on that. I guess currently, how much of that the sargassum is like? What is being done with that, and how is that kind of taken away? And and I'm just curious about kind of also how long it takes to actually manufacture the material to a point where you can actually use it in structure.
Okay, so it was not that long to do, mainly because it's very homemade. So Majo got like 2 or 3 kilos of sargassum, and then she like blended it and mixed it with cornmeal and glycerin. So it was like, I don't know, like maybe like some hours. Also, this material was sun-dried, so we didn't need any sort of some kind of energy to make it like go stiff. So it was not very like time consuming. It actually was very, very fast, and even faster than we expected. So yes, it's pretty simple to do and fast. Yeah.
Just to add to that, the time of sun drying, the material was about 3 days, but we just make it in a small scale. So to make that structures that we are planning, of course, it would take another time. And about the thing you said first of what are they making now with the sargassum, the amount of sargassum are a lot of them. So there are some projects that are also working with it, but really the problem is still 6 and it continues to exist. So the material is there. Yeah.
Oh, so sorry if it's getting too long, but also this sun drying time was because here it's rain season, so it's a little bit slower than it could be, right? But yeah, it's 2-3 days on a rainy day, but yes.
Great job, you guys. We are now going to go on to our last project of the day from McGill University. And then after that, we have a gallery show later in the day we'll remind you about later as well. So see all you guys there. So here is McGill's presentation.
Nature, in the broadest sense, refers to the general realm of all physical things. And although humans are part of nature, human activity is often viewed as a distinct category from other natural phenomena. For the more recent part of human history, our activities have been overwhelmingly destructive to the natural environments we inhabit. From a psychological standpoint, we justify these attitudes and proclivities by placing ourselves apart from everything around us. And yet, humans also have great capacity for empathy, compassion, and moral conscience. These more pro-social characteristics allow us to feel awe and reverence for nature, to care about the earth, and to seek harmonious coexistence with our natural birthplace.
Algae blooms are rapid accumulations in the population of algae, often recognized by the opaque green discoloration of water. They are caused by an increase in the levels of phosphorus and nitrogen, as well as high temperatures associated with global warming. These issues are compounded by human actions, with major contributors being agriculture, fertilizers, and industrial wastewater. World consumption of the three main fertilizer nutrients, nitrogen, phosphorus, and potassium, reached almost 195 million tons in 2020. The annual demand is only forecast to grow even further, and over the next 5 years, the global capacity of fertilizer production is also expected to increase. The most commonly used nitrogen and phosphorus-based fertilizers can often leach into the groundwater and be washed out into waterways. While algae is vital to ecosystems in normal amounts, algae blooms have a detrimental impact on the environment, contributing to ocean dead zones by depleting dissolved oxygen as they decompose, reducing other species' access to nutrients and sunlight, and sometimes even releasing toxins that can foul potable water supplies.
Common methods to control the population of algae that are currently in use involve chemicals or ultrasonic waves. These temporary solutions to algae blooms are often very expensive, can have harmful effects on other marine organisms, and can detrimentally disrupt ecosystems by completely killing off the algae. Our revolutionary solution is Algo, a large-scale device designed to collect excess algae from any body of water and take advantage of this resource by converting it to usable biomass.
Algo starts by pumping in water through a lily pad-inspired structure and then proceeds to extract the algae using a combination of flocculation and centrifugation. The combined effects of these dewatering methods increases the efficiency of cell harvesting and prepare the algae for lipid extraction. Using a method known as transesterification, lipids are drawn from the algae and ready to be used as bio-oil or biofuel. A filter mesh prevents unwanted elements from going into the submersible pump, and small elements that do enter, such as microplastics, should have minimal effects on the final product given the extraction process. To maintain sustainability throughout the design, the main source of power for Algo are solar panels running around the top of the device. Algo is also equipped with sensors to determine the tank capacity after the dewatering step, to alert users when the tank is full and when the final product is ready to be removed.
Our method of algae collection is therefore a safer method to reduce algae populations in bodies of water than current techniques. Furthermore, Algo takes things one step further by making the collected algae usable as biofuel or a sustainable substitute for fertilizer. Due to their renewable sources and biodegradability, biofuels are far less environmentally impactful than non-renewable fossil fuels. In the case of Algo, the constant supply of algae collected from the blooms provides the source of biofuel. Moreover, since algae removes and stores CO2 and volatile organic compounds from the air, using the algae as fuel releases only those previously removed pollutants, creating a net zero emissions energy source. Using the collected algae as fertilizer, on the other hand, is beneficial because it can be broken down to release these abundant sources of nitrogen, which can help grow crops efficiently.
In order to validate alga's ability to make a lasting impact on sustainability, several parameters will need to be verified. First, its effectiveness in reducing algae population would have to be measured. This can be done by testing algae concentrations in a body of water before and after using algal. Second, further tests involving the health of the ecosystem could include noting a change in the population of other aquatic species and determining whether the pump and filter are harming other organisms. Since mineral-rich fertilizers continue to be used and warm temperatures are present in most places, algal blooms will tend to return unless algal works periodically. We foresee a continuous supply of algae biomass that can be used to produce biofuels competitive against fossil fuels. By creating a synergy between these components, algal has the potential to help preserve the natural balance of aquatic ecosystems, generate clean energy, and offer a sustainable substitute to commercially available fertilizer. As humans, we have the potential to continue to blossom our more pro-social selves into prominence over time, so that we become less destructive and less apart in our self-conceptions. With algal, we can take a formidable step towards a harmonious coexistence with our natural birthplace, without compromising our need for progress.
Hi, everyone from the Algo team. Thanks for joining us. A great presentation. I'm going to hand it over for the last time to the judges for any questions. Fred, thank you.
Okay, well, I was just curious whether you went further than design on paper of this equipment.
Yeah, so actually we are starting to test out, so we have ordered cultures of algae, the most common strains, so that would be the C. vulgaris, and we have started to test the extraction process. So that would be the flocculation using nanochitosan and the centrifugation, which follows to completely extract the algae. And then separate from that, we have also started testing different pumps in order to make sure that we have the best system possible. So that's where we are at right now.
And just to follow up, have you considered, like the efficiency of extracting the algae with your machine compared to a collection of the algae and then doing this on land, for example?
So we wanted our device to be continuous in order to have that place in water and be able to continuously moderate the algae blooms. In our research, a combination of flocculation and centrifugation was the best method to extract algae. We also consulted an expert on algae cultures who guided us towards this path.
Thank you very much.
Great. Anyone else have a question today? Oh, Anya, you can go. Anya.
Hello. There's a lot of promise and interest in algae, and a number of years, number of decades. One thing that seems to hold it back is cost. And I was just wondering, did you all get to some sort of cost estimate? How cost competitive would you be when it comes to biofuels or fertilizer? Both things are kind of like very price sensitive, I think.
I think one of the main costs that when we looked into the cost of biofuel production is the cost to extract the algae in an efficient manner, whether that's the manual labor required or the potential impact that the methods used have on the system. So for us, we're lowering those regular costs by having a device that works fairly autonomously and can be used over and over again. The initial production cost right now appears to be around 3,000 Canadian dollars, but that's our first prototype, and the expectation is that the cost of the device itself will be decreased once we have a better supply chain in place and have finalized a couple of details.
And do you have like an understanding of like the $3,000 per, like how many kilograms, or would that get you, or how much product would that get you? Just trying to get to a ballpark price.
So like to answer that, it really just depends on the main factor that we have to consider in terms of the biomass collection is, first of all, the amount of algae that is present in the water body itself. So since our device is periodic, and it's not like a one-time use device, it keeps pumping algae into the system and then pumping out biomass. It just depends more on the water body than the actual product itself, because I mean, we obviously have to do wear and tear and durability tests. But from my understanding, since it's a periodic machine, it really just depends on how much algae is available in the body of water. And as far as numbers go, I think there are sources that suggest that about an acre of algae can produce about 10 to 15,000 gallons of fuel. So it really just depends on how much resources available sort of at baseline in the water body.
Thanks for elaborating.
Great, thank you. Leslie, did you have a question?
Yeah, hi. I really like the way that you take the algae, which is caused by fertilizer runoff, and use it for fertilizer. So that's really beautiful. My question is, how well does it work as fertilizer? Did you investigate that? And does it work as well as nitrates, and or have you done some research on there? Is there research on that?
Yeah, so research suggests that biofertilizers are able to increase nutrient availability in the soil very well, or mobilize the existing nutrient availability in that soil. So the main barrier at the moment is the cost, which, as I mentioned earlier, is directly correlated to the ease of extraction, and we're hoping to address that problem.
Excellent. Okay, thank you.
Wonderful. Well, I think we're going to wrap up for the projects today. Thank you, Algo team. You can turn off your cameras, and we will see you later at the gallery show. Dina, did you want to make some closing remarks with me?
Yes, of course. Thank you. Thank you, everyone, for joining us for day one. It was a pleasure for Emma and me to MC this first day. It was a long day. I feel it. But thank you for all of your work, and we'll see you later this evening, or wherever you are, whatever time it is. We'll have more presentations tomorrow starting at 1:30 p.m. Eastern time, Eastern New York time. But until then, please do join us for the virtual gallery show, which is going to start very, very soon at 3 p.m. Eastern time, New York time. You can find all of the information on the BDC Summit page. It links out to our gallery show. We have a few different sessions for throughout the night. So yeah, we hope to see you there. Anything else, Emma?
Yes, and everyone, don't forget to cast your vote for which Biodesign Challenge 2021 project you think should win the Community Choice Prize. You can vote on that through our website. If you visit, you'll see a link to a form. Voting will end on Thursday, June 24th at 12 p.m. Eastern, also New York time. And then finally, once again, please check out our Kickstarter page that we launched this morning, for our new book, Biodesign Challenge, a retrospective. We really hope you can support. You can get a discount right now if you order within the first 24 hours. And I believe that's all I have to say. Thank you, everyone. Leslie, did you have something you'd like to add?
We will be deliberating in about 15 minutes. Is that right? The panel.
We'll send more information via the Slack. We're live to the public right now, so we'll.
Okay. Very good. All right. Thank you. All right.
All right. Well, thank you again, everyone. Thank you, judges and students. We're really excited to see some more projects tomorrow and on Wednesday. Have a good one.
Take care.
Thank you.